The universe has presented one of its most important findings. With the advanced capability of the James Webb Space Telescope, astronomers have detected what may be the earliest galaxy ever observed, a system that formed when the universe was only a very small portion of its current age. The light from this distant galaxy began travelling more than 13 billion years ago, long before the Sun, the planets, or the Milky Way existed. Could this discovery stand as one of the most significant achievements in modern astronomy? Does it give scientists a direct view of the universe during its earliest stages after the Big Bang, and offers new information for understanding how everything began? Before we begin, like and subscribe to our channel, and let us know in the comments below where in the world you're watching from. We're always eager to hear where our viewers are tuning in from. Astronomers working with the James Webb Space Telescope have recently come across something that has left many of them confused, excited, and deeply curious. While going through enormous sets of images collected from different parts of the sky, they noticed an object that behaved in a way they could not easily explain. This unusual object has been given the name Capitauro, and many experts already describe it as one of the most puzzling and surprising discoveries they have ever seen. Even though astronomers regularly find strange objects scattered across space, this one stands out because its characteristics do not neatly fit into any known category. It appears too bright to be something small and too compact to be something large, and the details uncovered so far only raise more questions instead of giving clear answers. The James Webb Space Telescope, often called JWST, has been operating since the month of December in the year 2021, and it has delivered some of the deepest and most detailed observations of the universe ever recorded. With its advanced instruments, especially its infrared detectors that can capture light that has been stretched across billions of years, it has helped astronomers look farther back in time than any telescope before it. Because light takes time to travel, observing faraway objects allows scientists to see events that happened when the universe was very young. The farther they look, the closer they get to seeing the first stars and galaxies that appeared shortly after the universe began, roughly 13,800 million years ago. While analysing these deep-field images, a team of researchers noticed Capitauro because it was unusually bright for its size. Brightness in astronomy often helps scientists identify the nature of an object. Galaxies, for example, shine brightly because they contain billions of stars. Stars shine because of nuclear fusion taking place in their cores. Planets do not shine on their own, and brown dwarfs, the strange objects that fall between planets and stars, normally emit only faint levels of light. Capitauro, however, did not seem to match the typical behaviour of any of these categories. It was bright in a way that suggested something powerful was happening, but not in the exact way that a young star, an old star, or a small galaxy normally behaves. According to the first scientific paper submitted on this discovery, one possible explanation is that Capitauro might be a galaxy that formed only about 100 million years after the Big Bang. If this turns out to be correct, it would mean Capitauro existed at a time when the universe was still extremely young, still forming its earliest stars, still cooling, and still changing rapidly. No confirmed galaxy has yet been found that formed so early, and discovering one would dramatically change what scientists know about how fast structures formed in the ancient universe. If Capitauro is truly a galaxy from that period, it would be the earliest known galaxy ever observed by human beings. To understand how extraordinary this possibility is, astronomers point out that galaxies take time to form. First, clouds of gas must gather together under the force of gravity. These clouds then break apart into clumps that eventually form stars. After that, those stars grow, burn fuel, shine, and gradually build a structure that becomes a recognizable galaxy. All of this usually takes time. Many scientists believe that the universe needed several 100 million years before galaxies of any noticeable size could take shape. If Capitauro really dates back to around 100 million years after the Big Bang, then it means galaxies formed far earlier than previously expected. This would force experts to rethink many theories about the earliest eras of cosmic history. However, the story is not so simple. Other data gathered from the James Webb Space Telescope suggest that Capitauro might not be a galaxy at all. Instead, it could be a type of brown dwarf, which is often described as a failed star. A brown dwarf forms in a similar way to a star, starting as a cloud of collapsing gas. But instead of gaining enough mass to start nuclear fusion, the process that makes stars shine brightly, a brown dwarf stops growing before reaching that critical point. As a result, brown dwarfs glow only faintly, mostly in infrared light, and their temperatures remain relatively low compared to stars. Most brown dwarfs are only a few hundred to a few thousand degrees Fahrenheit. Kappa Tau, based on the data, seems to glow at a temperature of only about 80 degrees Fahrenheit, which is roughly 27 degrees Celsius. This is extremely cold for any object that shines on its own. For comparison, the surface of the Sun is around 10,000 degrees Fahrenheit. Even the coolest known brown dwarfs are usually still at temperatures comparable to a hot oven. Something glowing at 80 degrees Fahrenheit should not normally appear as bright or as detectable as Kappa Tau appears in the Webb images. This is one reason astronomers are unsure whether it truly is a brown dwarf. Another complication is Kappa Tau's location. If it were a galaxy from the early universe, it would be positioned billions of light years away, meaning its light would have been travelling toward us for more than 13 billion years. But if it is a brown dwarf located on the outer edges of the Milky Way, it would be much closer, possibly only a few thousand light years from Earth. These two explanations place the object in completely different regions of space, separated by unimaginable distances. Understanding which location is correct is one of the biggest challenges in identifying Kappa Tau. The reason for this confusion is found in the way the James Webb Space Telescope analyzes light. When light from a distant object reaches the telescope, it can be stretched or redshifted due to the expansion of the universe. Objects that are very far away show extremely high redshifts, making their light appear in longer wavelengths. However, some nearby objects can also produce infrared light that looks similar to redshifted light, depending on their temperature and composition. This overlap can sometimes trick even the most advanced instruments. Kappa Tau sits right in that difficult zone where a very distant galaxy and a nearby, unusually dim star-like object can look strangely similar. The team studying Kappa Tau has been cautious. They have emphasized that its identity remains uncertain. The early data lean in two possible directions, each equally fascinating. In one scenario, Kappa Tau could be the youngest and earliest galaxy ever observed, one that formed when the universe was just beginning to take shape. In the other scenario, it could be one of the coldest and most unusual brown dwarfs ever recorded, located far out on the outskirts of our own galaxy, in a region where stars become rare and space grows increasingly empty. If Kappa Tau is a galaxy, then it must have an enormous amount of energy for something that young. Young galaxies usually shine brightly because they are home to many new stars. These stars form quickly from dense clouds of hydrogen and helium, which were the main elements present in the universe shortly after the Big Bang. These early stars tend to be very large and burn extremely hot, making them bright even if they live for only short periods of time. If Kappa Tau is one of these early structures, then it might contain some of the first generations of stars ever formed. Studying these stars would offer scientists a rare opportunity to understand the earliest stages of cosmic evolution. On the other hand, if Kappa Tau is a brown dwarf, then it would challenge what astronomers currently know about such objects. A brown dwarf with such a low temperature should not be bright enough to stand out in deep space images. It would need to be much closer to the Earth for the telescope to detect it so clearly, yet the brightness levels do not perfectly match the behaviour of a nearby object. This means that if Kappa Tau is indeed a brown dwarf, then it must have some properties that scientists did not expect. It might have an unusual chemical composition that makes it glow in a special way, or it might be surrounded by gas or dust that reflects infrared light unexpectedly. There is also the possibility that Kappa Tau represents something entirely new, something that does not fit neatly into known categories. Astronomers are cautious about claiming such things, because history shows that unusual objects often turn out to be examples of something already known. But at the same time, the universe is vast, and there is no reason to assume humanity has discovered every kind of object that can exist. Kappa Tau could be one of those rare discoveries that expands scientific understanding by revealing a new type of celestial body. Another detail that has drawn attention is Kappa Tau's brightness pattern. Astronomers use a technique called a spectral analysis to break apart the light coming from an object and examine the wavelengths that make it up. These wavelengths act like a fingerprint, showing what elements are present or how fast the object is moving. When Kappa Tau's spectral data were examined, they did not show a typical galaxy shape, nor did they show the usual patterns associated with stars or brown dwarfs. Instead, the data appeared strange, with unusual dips and peaks. Some of these could come from dust, some from gas, and some from processes that are not yet fully understood. The team handling the observations has stressed the importance of patience. Scientific discovery often requires repeated measurements, cross-checking, and careful analysis. The James Webb Space Telescope has provided one of the deepest and most sensitive views ever achieved, but even so, interpreting its data is complex. Some of the earliest galaxies detected by the telescope in its first year of operation were later confirmed, but others turned out to be smaller, closer, or simply different than first assumed. Capitaro might follow a similar path, where early assumptions gradually give way to a more accurate picture as more information becomes available. Some astronomers argue that the galaxy interpretation makes more sense because of Capitaro's brightness. Objects that are extremely far away need to be incredibly bright for their light to reach us after travelling across nearly the entire history of the universe. Something from 100 million years after the Big Bang would need to shine very strongly to be visible today. Capitaro's brightness fits this requirement, making the galaxy explanation appealing. But the unusual spectral signature still leaves room for doubt. Galaxies usually show signs of star formation, dust, and certain elements. Capitaro's data do not clearly show these features, though this might be because the object is extremely young. Other researchers lean toward the brown dwarf idea. They point out that the brightness fluctuations could come from the surface of a brown dwarf that has different temperature zones. Some brown dwarfs have patchy atmospheres of swirling gas, with hot and cool regions. As these regions rotate, the brightness of the brown dwarf can change slightly. Capitaro shows patterns that could match such activity, especially since its light varies over time. Still, the incredibly low temperature of 80 degrees Fahrenheit remains difficult to explain, making some experts hesitate before accepting this explanation. In recent years, brown dwarfs have become a major area of study. Thousands have been identified, but only a few have been detected with temperatures below 100 degrees Fahrenheit. These cool brown dwarfs, sometimes called Y dwarfs, are extremely faint and hard to find. Discovering one at the far edges of the Milky Way would be surprising because most known brown dwarfs are found much closer to the Sun, within a few dozen light years. If Capitaro is a brown dwarf located thousands of light years away, it would be the farthest and one of the strangest of its kind. The fact that Capitaro lies in such a difficult region of the sky only adds to the puzzle. It sits in an area where the James Webb Space Telescope has detected other faint objects that appear to come from the early universe. This makes the galaxy explanation attractive, but mixed in with those distant objects are faint stars, brown dwarfs, and other nearby bodies that sometimes mimic the appearance of ancient galaxies. Separating one type from another requires precise measurements, and even small errors can lead to large misinterpretations. As the research continues, astronomers are requesting more observation time with the telescope. Additional data from different instruments, wavelengths, and angles could help determine whether the light from Capitaro is stretched by the expansion of the universe or produced by a nearby object. The team is also comparing the object with models created using computer simulations. These simulations help researchers see what early galaxies might have looked like and how brown dwarfs behave under different conditions. By matching the data from Capitaro with these models, they hope to find the closest fit. Many astronomers who have not directly worked on the study are still eager to follow the results. The possibility of discovering the earliest known galaxy is thrilling. Such a discovery would give the scientific community new clues about how quickly stars formed after the universe began. It would also help explain how the first galaxies grew, merged, and evolved into the giant systems seen today. On the other hand, the possibility of finding an unusually cold and distant brown dwarf is equally interesting, because it would reveal new things about the outer structure of the Milky Way, where relatively little is known. Some researchers have even wondered whether Capitaro might be part of a larger population of mysterious objects that have simply never been detected before. The James Webb Space Telescope is powerful enough to reveal things that older telescopes like the Hubble Space Telescope could not see at all. It is possible that there are thousands of faint, unusual, or confusing objects scattered across the sky that will only now begin to appear in the data. Capitaro might be the first of many such objects that challenge long-established ideas. Regardless of its final classification, Capitaro has already influenced scientific discussions. Researchers are debating what the discovery means for telescope surveys, how they should interpret faint infrared objects, and whether their models of early galaxy formation need adjustment. Some argue that the early universe may have formed stars far more quickly than expected, while others think that new types of stars or brown dwarfs might exist that have never been seen before. At the centre of this debate lies the simple truth that Kapataro's identity is still unknown. The data collected so far show an object that does not behave like anything that perfectly fits into existing categories. It is bright but does not shine like a typical star. It is compact but lacks the usual features of a small galaxy. It is warm enough to glow but strangely cool compared to nearly all other glowing objects. It sits in a location that could support either explanation. All of this makes Kapataro one of the most captivating mysteries revealed by the James Webb Space Telescope so far. More data will come in the months and years ahead, and scientists expect that eventually the mystery will be resolved. But for now, Kapataro remains suspended between two possible identities, each more fascinating than the other. Whether it turns out to be an extraordinarily early galaxy born during the universe's youth, or an unusually cold and distant brown dwarf on the edge of the Milky Way, it is already a discovery that has captured the imagination of astronomers around the world and opened new paths of investigation into the structure and history of the cosmos. The possibility that the James Webb Space Telescope has finally caught sight of population 3 stars has filled astronomers with a sense of excitement that is difficult to put into ordinary words, because these stars represent something far deeper than merely bright objects in space. They are believed to be the very first generation of stars ever born in the universe, forming when the cosmos itself was extremely young and when matter had only just cooled enough to begin gathering under the pull of gravity. Every star we see today, every planet, every cloud of gas and even the atoms inside our own bodies can be traced back, in one way or another, to the heavy elements that later generations of stars made. But population 3 stars came before all of that. They existed in a time when the universe had nothing except hydrogen, helium, and the mysterious presence of dark matter, and so they lived in an era completely different from anything we can witness in the modern universe. Any detection of these stars, or even a cluster of such stars, is like catching a moment from the earliest chapters of cosmic history. Astronomers working with the extremely powerful James Webb Space Telescope may have identifying evidence that some of these ancient stars have been found in a distant cluster known as LAP-1b. This faint object lies roughly 13 billion light-years from Earth, meaning that the light from it began travelling toward us when the universe was only a small fraction of its current age. It is remarkable that we are able to see anything at such a distance, yet the James Webb Telescope was designed specifically so that humanity could peer this far into the past. Its enormous mirror measures 6.5 meters, which is about 21 feet across, allowing it to collect exceptionally faint light that older telescopes would never detect. But size alone is not the only thing that made this discovery possible. The universe itself provided additional help through an effect predicted long ago by Albert Einstein, known today as gravitational lensing. When a massive object sits in front of a distant source of light, space-time bends around the massive object, causing the background light to be distorted, stretched, or magnified. If everything lines up with extraordinary precision, the distant object can appear much brighter, or in a different shape than it normally would. Astronomers often refer to this effect as an Einstein ring or an Einstein arc, depending on whether the background object is stretched into a circular shape or a long arc. In the case of LAP-1b, it became visible because a foreground galaxy cluster called MAX J0416 moved into just the right position and acted like a natural cosmic magnifying glass. Without this gravitational lensing, the cluster containing the potential population 3 stars would have been far too faint for even the James Webb Telescope to detect. The fact that the universe occasionally lines up like this allows astronomers to study some of the earlier stages of cosmic evolution. Population 3 stars have long existed only in theory, because no one had ever definitively seen a pair, a cluster, or even a single one. These stars are sometimes described as dark stars, not because they are dim, but because they formed in an age with no heavy elements, and so they behave differently from stars that formed later. All stars we see today are filled with elements such as carbon, oxygen, nitrogen, and iron. Even if those amounts are extremely small, these elements were created by earlier generations of stars. But population 3 stars formed when the universe was made almost entirely of hydrogen and helium, and so they burned extremely hot and extremely fast, The lack of heavier elements allowed them to grow to tremendous sizes, possibly reaching masses 100 times greater than the mass of the Sun, or in some theoretical cases even reaching as much as 1 million times the mass of the Sun. Their brightness may have been astonishing, potentially 1 billion times brighter than the Sun in some predictions, illuminating the young universe long before galaxies took on the stable shapes we see today. Because these stars lived in such a distant and ancient era, scientists have had to rely on indirect clues to know what to look for. One key clue is the spectral signature of the light. When stars burn, they emit light at certain wavelengths depending on their temperature and composition. This light, when stretched across great distances, is shifted into different wavelengths because the universe is expanding. What begins as ultraviolet radiation can be shifted into the infrared by the time it reaches us. The James Webb Telescope is built specifically to measure infrared light with exceptional sensitivity, making it ideal for detecting early universe objects. Eli Visbal, the lead author of the study and an associate professor of astrophysics at the University of Toledo in the state of Ohio, explained that the spectral lines observed from LAP-1b share several features predicted for population 3 stars. These stars are expected to emit enormous numbers of high-energy photons because they burn so hot. When the researchers analysed the emission lines from the light captured by the telescope, they found the signatures of these high-energy photons, suggesting the presence of extremely massive and extremely hot stars. The spectra also suggested that the stars had masses around 100 times the mass of the Sun, fitting well within the theoretical expectations of some population 3 models. According to Visbal, if these stars really are population 3 stars, then this would be the first confirmed detection of primordial stars in the entire universe. This would represent a major breakthrough, because for decades astronomers have searched for any trace of these earlier stars, yet the universe is so large and so many of these stars have died that clear evidence has been difficult to find. Earlier studies using the James Webb Telescope have suggested possible population 3 stars before. For instance, in March of the year 2024, peer-reviewed research argued that the telescope may have spotted such stars in the galaxy known as GNZ11, which formed only about 430 million years after the Big Bang. But the new study argues that the evidence in LAP-1b is stronger and more consistent with theoretical expectations. The researchers explained that LAP-1b meets 3 separate theoretical conditions that population 3 stars must satisfy. First, the stars must form in an environment with extremely low metallicity. In astronomy, the term metallicity refers to the amount of elements heavier than hydrogen and helium in a star or a gas cloud. Population 3 stars must have formed in an environment where almost no heavy elements existed, because the early universe had not yet created any. The observation suggests that LAP-1b formed in such an environment, containing only hydrogen and helium, a crucial requirement for confirming these are primordial stars. Second, the stars must form in clusters with only a small number of extremely large stars present. The theory suggests that because the early universe lacked heavy elements, the gas could collapse into fewer but much larger stars. Modern clusters form large numbers of smaller stars, but early clusters would have been small in number yet enormous in size. The LAP-1b cluster appears to fit that pattern, a relatively small cluster with only a few huge stars dominating the light. This supports the idea that this cluster belongs to the very first generation. Third, the stars must satisfy the mathematical rules of something known as the initial mass function. This is a concept astronomers use to describe how masses are distributed among stars when they first form. For population 3 stars, theories predict a very different distribution from modern star-forming clusters. The stars should be heavily skewed toward extremely large masses, unlike the evenly spread distribution in the modern universe. LAP-1b appears to match this predicted distribution closely, making it a particularly strong candidate for containing true population 3 stars. Visbal emphasized that none of these observations would have been possible without the James Webb Telescope, not only because of its size, but also because of its ability to detect infrared light. When the universe expands, wavelengths of light stretch. Light that population 3 stars originally emitted in ultraviolet wavelengths has been stretched over billions of years until it arrives as infrared light. The James Webb Telescope is optimized for these wavelengths. Older telescopes, such as the Hubble Space Telescope, were extremely powerful, but were not designed to pick up trace infrared signatures from the earlier stars. The James Webb Telescope not only detects such wavelengths, but does so with clarity and detail that allow scientists to analyze specific emission lines and reconstruct the chemical and physical properties of the stars. The gravitational lensing effect provided by the foreground galaxy cluster, MAX J0416, made the cluster appear brighter and clearer than it otherwise would. The bending of spacetime magnified LAP-1b, allowing the light to be dissected and studied. Without this lensing, the cluster's light would be too faint to gather meaningful data from. This combination of the James Webb's design, its enormous sensitivity, and the natural lens provided by the universe allowed astronomers to effectively pull a moment out of the first few 100 million years after the Big Bang. The possibility that LAP-1b contains genuine population 3 stars has deeper consequences than simply identifying ancient stars. It offers an extraordinary opportunity to understand how galaxies formed in their earliest stages. Population 3 stars are thought to have been born inside small dark matter structures known as mini-halos. These mini-halos were extremely small compared to modern galaxies, yet they played a key role in building the larger galactic structures that exist today. The earliest stars not only contributed their light, but also began the process of chemical enrichment. They created heavier elements through nuclear fusion in their cores and through the explosions that occurred when they died as supernovae. The heavy elements that filled the universe later came from these large explosions. The universe started out with only hydrogen and helium, but the death of population 3 stars began to change that, slowly adding carbon, oxygen, nitrogen, iron, and many others into the cosmic environment. These elements later cooled into clouds and eventually formed planets, asteroids, and all forms of life. The newly observed cluster provides clues about this important transition. By analysing the emission lines and the expected lifespan of massive stars, astronomers can estimate how long population 3 stars may have lived before collapsing. These stars likely lived very briefly on cosmic timescales, possibly only a few million years. Because they were so massive, they burned through their nuclear fuel extremely rapidly. This means that observing them is extraordinarily rare, because they disappeared long before galaxies fully developed. The fact that LAP-1b appears in a time frame where population 3 stars would still exist suggests that astronomers are looking at an extremely brief but profoundly important moment in cosmic evolution. The presence of population 3 stars also helps determine how quickly the universe became enriched with metals. Different models suggest different speeds. Some models propose rapid enrichment from extremely massive stars, while others propose a slower process. Observing the chemical state of LAP-1b sheds light on whether the enrichment happened quickly or whether it took longer for the first heavy elements to spread through the early universe. The fact that LAP-1b appears to contain almost no metals tells astronomers that they have caught the universe before heavy element enrichment began in that particular region. Because population 3 stars are expected to disrupt their environment significantly, the study of LAP-1b also gives insight into how early stars influenced their surroundings. Massive stars produce intense ultraviolet radiation, which can ionize gas around them, changing the temperature and structure of nearby regions. This feedback affects how additional stars can form, shaping the evolution of small early galaxies. By studying the shape and composition of LAP-1b, astronomers can determine how strong these feedback effects were, and how early galaxies may have grown or collapsed under the influence of the first stars. The discovery also has implications for understanding dark matter. Population 3 stars are believed to form in dark matter halos, meaning their distribution, size, and lifespan help scientists test models of how dark matter behaves. Dark matter does not emit light and cannot be directly observed, but it reveals itself through gravitational effects. The structure of LAP-1b and its alignment with theoretical expectations strengthen certain dark matter models and help eliminate others. The fact that LAP-1b is so distant and so ancient makes it a perfect natural laboratory for studying dark matter behavior during the earliest formation periods of the universe. As more data from the James Webb Telescope becomes available, scientists hope to find more clusters like LAP-1b. If additional examples of population 3 star clusters can be identified, astronomers will be able to compare them, refine their theories, and build a clearer understanding of how the early universe evolved from a simple cloud of hydrogen and helium into the complex web of galaxies, stars, and planets seen today. The more clusters found, the more patterns will emerge about early star formation rates, masses, lifespans, and the role of dark matter in shaping the cosmic structure. The discovery has also encouraged scientists to revisit older observations that might have been overlooked. Some light sources previously dismissed as too faint or too indistinct may now be re-examined with the possibility that they contain population 3 stars. Because the James Webb Telescope sees deeply into the infrared, many ancient objects appear differently than astronomers expected. The telescope has repeatedly surprised researchers by revealing galaxies that were larger, more fully developed, or brighter than theoretical models predicted for the early universe. LAP-1b adds to a growing list of discoveries that show the early universe was more dynamic and filled with activity than once believed. The idea that these first stars were enormous, bright, and short-lived provides a sense of just how different the early universe was from today. Modern stars, including our Sun, are made of multiple elements and follow a stable evolutionary path. Population 3 stars were far more extreme, forming rapidly in harsh environments where gases were hotter, pressures were different, and cooling mechanisms were limited. The discovery of possible population 3 stars gives scientists the chance to study physics under conditions that cannot be reproduced anywhere else. Every new piece of data about these stars fills in some of the missing history of the universe. Observing LAP-1b also shows how closely theory and observation can work together. For decades, population 3 stars existed only in computer models and mathematical descriptions. Astronomers predicted their temperatures, masses, spectra, and lifetimes, but no one had evidence that such stars had ever been captured in real data. Now, with LAP-1b meeting multiple theoretical requirements, the scientific community has strong grounds to believe that it is seeing, for the first time, light from a generation of stars that helped shape everything that came after. Because population 3 stars are linked to cosmic reionization, the process during which the universe transitioned from being filled with neutral hydrogen to ionized hydrogen. LAP-1b may also help scientists determine when and how reionization began. This transition fundamentally changed the transparency of the universe, allowing light to travel freely. Understanding which stars contributed to this transformation, and when they did so, is crucial to completing the timeline of cosmic history. The intense ultraviolet radiation expected from population 3 stars is believed to have played a major role in this important era. Visbal noted that observing details such as the emission lines from LAP-1b helps astronomers better understand how the earlier stars influenced the formation of later galaxies. The heavy elements created by the earlier stars spread through the interstellar medium, eventually cooling and forming new star-forming regions with different characteristics. This cycle, repeated for billions of years, gradually led to the variety of galaxies observed in the modern universe. By studying this ancient cluster, astronomers gain direct evidence of the first steps in this long chain of cosmic events. The detection is still considered a candidate, meaning scientists need further confirmation. Yet the strength of the evidence is far greater than earlier attempts, making LAP-1b a powerful step forward. Future observations may help confirm whether the stars fall precisely within the expected temperature range of population 3 stars, whether they behave as predicted, and whether the cluster's environment truly matches the pristine conditions required. The discovery of LAP-1b also shows how much the James Webb Telescope E has transformed astronomy in such a short time. The telescope began operations in late 2021, and within only a few years it has already revealed galaxies from the early universe, detailed atmospheres of exoplanets, structures within distant nebulae, and now what appears to be the first direct evidence of population 3 stars. Its ability to see deeper, clearer, and farther than any telescope before it is rewriting chapters of cosmic history that scientists long believed were out of reach. The potential identification of population 3 stars within LAP-1b represents a moment when theory, observation, and the vast scale of the universe come together in a single discovery. These stars shaped the cosmos before galaxies took their final forms and before the universe became chemically diverse. They are ancestors to all later stars, including the one that warms Earth. Being able to detect their light after it has travelled for more than 13 billion years is a testament to how much humanity's understanding of the universe has progressed. If LAP-1b truly contains population 3 stars, then the light that reached the James Webb Telescope came from a time when the first stars were still forming from primordial hydrogen and helium. It is a direct connection to the earliest luminous objects that ever existed, a rare opportunity to witness the beginning of stellar history and the beginning of the cosmic processes that eventually made life possible. Astronomers have recently uncovered a fascinating and puzzling phenomenon in the depths of space, involving a planet that drifts alone without a star, yet consumes matter at a rate previously unimagined for such objects. Using the combined powers of the James Webb Space Telescope, known widely as JWST, and the Very Large Telescope in Chile, abbreviated as VLT, scientists have been able to observe this unusual world in unprecedented detail. The planet, designated CHAR 11077626, is classified as a rogue planet, a type of celestial body that wanders through the cosmos independently without orbiting a host star. While astronomers have catalogued numerous rogue planets over the years, CHAR 1107-7626 distinguishes itself by exhibiting an extraordinarily high rate of accretion, meaning it is actively pulling in and consuming gas and dust from the surrounding environment at an astonishing pace. Observations reveal that the planet is acquiring material at a peak rate of 6.6 billion tons per second, equivalent to 6 billion metric tons, making it the fastest growing free-floating planet ever documented. This finding has captivated researchers as it blurs the line between the processes of planet formation and star formation, two phenomena that were traditionally viewed as distinct. The discovery of CHAR 1107-7626 and its extreme behaviour stems from a series of careful observations that relied on the advanced instruments aboard JWST and the VLT. The European Southern Observatory operates the Very Large Telescope, which is stationed in the arid plains of northern Chile, an environment particularly suitable for astronomical observation due to its high elevation and low atmospheric interference. Meanwhile, the James Webb Space Telescope, orbiting far beyond Earth's atmosphere, provides unparalleled sensitivity to infrared light, allowing astronomers to detect objects that are otherwise invisible in ordinary visible light. Infrared detection is crucial in observing rogue planets because these objects do not emit visible light on their own in significant quantities. Instead, they glow primarily in infrared as they radiate leftover heat from their formation. By combining the capabilities of these two instruments, astronomers have been able to not only locate CHAR 1107-7626, but also monitor the variations in its accretion activity over time, revealing a dynamic and ever-changing process. The most striking feature observed in CHAR 1107-7626 is a phenomenon called an accretion burst. This event occurs when a celestial body suddenly ingests a large quantity of matter from its surrounding disk of gas and dust. Such disks are remnants of the formation process and serve as reservoirs of material that a planet or star can draw upon to grow. In the case of CHAR 1107-7626, the accretion is not steady, rather it fluctuates significantly. Observations conducted in August 2025 indicated that the planet was accreting at a rate 8 times higher than it had been a few months prior, demonstrating a sudden surge in its growth rate. These bursts are of particular interest because they closely resemble similar events observed in young stars, where sudden increases in accretion are thought to play a crucial role in their formation and evolution. The parallel between a rogue planet and a young star in this regard is both surprising and intriguing, prompting astronomers to reconsider the processes that govern the early development of planetary mass objects. The occurrence of accretion bursts in stars has been studied for many decades. The first such event was observed in the late 1930s, long before astronomers fully understood what they were witnessing. Today, scientists recognize that these bursts are essential to star formation, as they influence the growth of the star itself and also affect the surrounding material in which other planets may form. By heating the gas and dust in the nearby nebula, accretion bursts can alter the chemical and physical environment, shaping the conditions under which planetary systems eventually emerge. Alexander Schultz, a professor of astrophysics at the University of St Andrews in Scotland, and a co-author of the study, explained that accretion bursts may leave lasting signatures in the chemical composition of meteorites, suggesting that these violent yet fundamental events can influence even small bodies in a solar system long after the star or planet has stabilized. The observation of a similar burst in a planetary mass object like CHAR 1107-7626 raises the possibility that a universal mechanism underlies the behavior of both stars and planets during their early stages of formation. Understanding how and why these accretion bursts occur in rogue planets presents a significant challenge. Unlike stars, which are massive enough to sustain nuclear fusion and emit vast amounts of energy, rogue planets are considerably smaller and lack the internal mechanisms that drive the evolution of stars. This size difference raises important questions about the formation pathways of planets versus stars and where exactly these processes diverge. The fact that Char 1107-7626 can undergo rapid bursts of accretion, similar to young stars, suggests that there may be more overlap in the early development of these objects than previously assumed. It also opens the possibility that certain principles governing accretion and growth in the cosmos may operate across a wide range of masses, from the smallest planetary mass objects to the largest stars. Researchers are particularly interested in determining whether such bursts are common among rogue planets, or if Char 1107-7626 represents a rare and extreme case. By observing more rogue planets, astronomers hope to uncover patterns that will clarify the underlying physics of these events. Recent advancements in observational astronomy have facilitated the discovery of a growing number of rogue planets. The James Webb Space Telescope, for example, has identified over 500 such objects in a trapezoid-shaped region of the Orion Nebula, a vast and active star-forming region located roughly 1,350 light-years from Earth. The Orion Nebula is particularly notable for its dense clouds of gas and dust, which provide fertile ground for the birth of stars and planets alike. Despite these discoveries, rogue planets remain elusive due to their relatively low luminosity and the fact that they do not orbit stars, making them challenging to detect using traditional methods such as transit observations or radial velocity measurements. Instead, astronomers rely on infrared light to locate and study these objects. Infrared observations capture the faint glow emitted by the heat of the planet itself or by the surrounding accretion material, providing a window into processes that are otherwise invisible. Instruments like JWST and VLT are therefore indispensable for understanding the properties, behavior, and population statistics of free-floating planets. The accretion observed in Char 1107-7626 also sheds light on broader questions about planetary and stellar formation. While stars grow by pulling in material from their surrounding disks, planets are generally thought to form more gradually, either through the accumulation of solid bodies or by capturing gas from the protoplanetary disk around a star. Rogue planets, however, do not have a nearby star from which to draw additional material, which makes the high accretion rates observed in Char 1107-7626 particularly puzzling. It raises the question of whether these planets retain their own residual disks of gas and dust for extended periods, or whether they can capture material from interstellar clouds they encounter as they travel through space. The dynamic behavior observed, including the episodic accretion bursts, may provide clues about the physical and chemical conditions within these disks and how such conditions influence the ultimate mass and structure of the planet. Alexander Schultz emphasized that the study of accretion bursts in planetary mass objects like Char 1107-7626 could have far-reaching implications for our understanding of both stars and planets. If similar processes operate across different types of celestial objects, it may indicate that there is a fundamental universal mechanism at play in the early evolution of matter in the universe. This perspective challenges the conventional view that stars and planets form through entirely separate processes, suggesting instead that there may be a continuum of accretion behavior that spans a wide range of masses. By examining the details of these bursts, including their frequency, intensity, and impact on surrounding material, astronomers hope to refine models of star and planet formation, providing a more unified picture of how celestial objects grow and evolve over time. The discovery of Char 1107-7626 has already sparked interest in conducting follow-up observations. Almendros Abad, another member of the research team, noted that studying more rogue planets with instruments like JWST and VLT will help determine how common accretion bursts are among these objects. By building a larger sample of observations, scientists aim to quantify the role of accretion events in the evolution of planetary mass objects and understand whether Char 1107-7626 represents an extreme outlier or a typical example of rogue planet behavior. Observing the variations in accretion rates over time will also provide insight into the physical mechanisms that trigger bursts, such as gravitational instabilities within the disk, interactions with nearby material, or internal processes within the planet itself. Each new observation has the potential to refine theories and challenge existing assumptions about how planets form and grow outside of the gravitational influence of a star. The characteristics of CHA 1107-7626 also have implications for understanding the chemical and physical environment of the surrounding space. Accretion bursts are known to heat nearby gas and dust, potentially altering the composition of the material in the planet's vicinity. This process could influence the formation of additional planetary bodies, smaller moons, or other debris that may coexist in the same region of space. In our own solar system, relics of past accretion events in young stars may be seen in the chemical signatures of meteorites, providing a historical record of the dynamic processes that shaped planetary formation. Similarly, studying the effects of accretion bursts in rogue planets could reveal how these isolated worlds interact with their environment and how the energy released during bursts propagates through surrounding clouds of material. The observations of CHA 1107-7626 have not only expanded the known population of rogue planets, but have also challenged existing theories about their formation. Rogue planets were once thought to form primarily through processes similar to star formation, with gravitational collapse playing a major role, or through ejection from young planetary systems where interactions with other massive planets or stars could expel them into interstellar space. The extreme accretion observed in this planet suggests that additional processes may contribute to their growth, and that rogue planets can experience episodic bursts of mass accumulation even long after their initial formation. These findings provide a new perspective on the diversity of planetary formation pathways and underscore the complexity of growth mechanisms that operate beyond the influence of a parent star. Astronomers continue to explore the population of rogue planets throughout our galaxy, seeking to understand the prevalence and characteristics of these free-floating worlds. Infrared surveys conducted with JWST and VLT have already uncovered hundreds of candidates, but each new observation brings surprises, such as the dramatic accretion behavior seen in CHA 1107-7626. Researchers hope that by studying a larger sample of rogue planets, they can identify patterns in accretion behavior, determine typical mass ranges, and explore correlations with factors such as age, environment, and initial formation conditions. These efforts aim to build a more comprehensive picture of planetary evolution in isolation, expanding our understanding of how celestial objects develop under conditions that differ from the familiar context of a solar system orbiting a central star. The insights gained from CHA 1107-7626 also prompt questions about the broader implications for astrophysics. If rogue planets exhibit accretion bursts similar to those of young stars, it suggests that fundamental processes governing mass accumulation and energy release may operate universally across a wide spectrum of celestial objects. This idea challenges astronomers to refine existing models of star and planet formation to accommodate the dynamic and episodic behavior now observed in planetary mass objects. By studying the timing, magnitude, and effects of accretion bursts, scientists hope to uncover the underlying physical mechanisms and to determine whether these events follow predictable patterns or are largely stochastic in nature. Such knowledge may ultimately influence our understanding of the evolution of matter in the galaxy, from the formation of stars to the development of isolated planetary worlds. As research progresses, astronomers plan to conduct long-term monitoring of CHA 1107-7626 and other rogue planets to capture additional accretion bursts and to map variations in growth rates over extended periods. Continuous observation will help identify triggers and cycles in the accretion process, allowing scientists to test theoretical models against empirical data. Moreover, by comparing the behavior of rogue planets with that of young stars and planets within conventional star systems, researchers can explore the similarities and differences in growth mechanisms, providing a richer understanding of the forces shaping the cosmos. Each new burst recorded adds to a growing body of evidence that challenges preconceived notions about isolated planets and their capacity for dramatic star-like behavior. The extreme growth of CHA 1107-7626 also emphasizes the importance of advanced observational technologies in modern astronomy. Instruments such as JWST and VLT enable astronomers to detect subtle infrared signatures, track changes in accretion rates, and measure the composition of surrounding gas and dust with high precision. Without these tools, the dynamic and complex nature of rogue planets would remain largely hidden, leaving gaps in our understanding of planetary evolution. As telescopes become more sensitive and techniques for analyzing data improve, the study of rogue planets and other faint celestial objects will continue to reveal unexpected phenomena, reshaping our knowledge of how the universe operates on both small and large scales. Observations of CHAR 1107-7626 have also sparked discussions about the boundaries between planets and stars. The similarities in accretion behaviour suggest that there may not be a strict dividing line between these classes of objects, at least in terms of their early growth processes. Instead, there may be a continuum of mass and behaviour, where small planetary mass objects can exhibit processes previously associated only with more massive stars. This perspective encourages astronomers to consider a broader range of possibilities when modelling the formation and evolution of celestial bodies, taking into account episodic growth, environmental influences, and interactions with surrounding material. The study of accretion bursts in rogue planets like CHAR 1107-7626 continues to be a vibrant and rapidly developing area of research. Each observation provides valuable data that informs theories of planetary formation, mass accumulation, and the behaviour of isolated celestial objects. As the catalogue of rogue planets grows, and as more bursts are detected and analysed, astronomers hope to piece together a more coherent picture of how these worlds develop in the absence of a host star. Understanding the similarities and differences between the accretion processes of stars and planets could ultimately lead to a deeper comprehension of the universal principles that govern the evolution of matter in the universe. The insights gained from CHAR 1107-7626 may also influence future explorations of star-forming regions such as the Orion Nebula, where large populations of rogue planets have been found. By studying these objects in detail, astronomers can investigate how interactions within dense nebular environments affect the growth and development of isolated planets, and how episodic accretion events contribute to the overall dynamics of such regions. Moreover, continued observation may reveal previously unknown mechanisms that allow rogue planets to maintain high rates of accretion over extended periods, offering a more nuanced view of planetary evolution in extreme conditions. The continued analysis of CHAR 1107-7626 and other rogue planets also provides a framework for comparing isolated planetary systems to those that exist within the gravitational influence of a star. By examining differences in mass accumulation, accretion variability, and environmental interaction, astronomers can identify the key factors that differentiate planetary evolution in isolation from that within conventional systems. This comparative approach may shed light on the broader processes governing planetary formation throughout the galaxy, and inform models of planet occurrence rates, growth patterns, and long-term stability. Observations to date suggest that CHAR 1107-7626 may represent a key case study in the investigation of planetary accretion bursts, illustrating how isolated worlds can undergo rapid and dramatic growth, similar in some respects to young stars. These findings underscore the dynamic nature of the universe and highlight the need for continued exploration, using advanced infrared telescopes, long-term monitoring, and sophisticated analytical techniques. By capturing and analysing the episodic accretion behaviour of rogue planets, astronomers are uncovering new layers of complexity in the processes that shape celestial bodies, challenging traditional classifications and expanding our understanding of planetary and stellar evolution alike. CHAR 1107-7626 exemplifies the potential for rogue planets to defy expectations, demonstrating behaviours once thought exclusive to stars and providing a valuable opportunity to study extreme planetary growth in situ. As JWST and VLT continue to observe these objects and other emerging discoveries across star-forming regions, astronomers anticipate that additional rogue planets will reveal similar or even more extreme accretion phenomena, offering further insight into the mechanisms that drive growth in isolated planetary systems. Each new observation contributes to a richer understanding of the universal principles that govern accretion, mass distribution, and the evolution of matter across the cosmos, bridging gaps in knowledge and expanding the frontiers of planetary science. The discovery of CHAR 1107-7626 and its extraordinary accretion activity has fundamentally enhanced scientific understanding of how planetary mass objects can develop independently of a star. The unprecedented growth rates observed demonstrate that even small, free-floating planets can undergo dynamic, episodic bursts of material accumulation, challenging assumptions about the limitations of planetary evolution. By continuing to monitor these events and studying additional rogue planets, astronomers aim to uncover the prevalence, mechanisms, and long-term impacts of accretion bursts, further elucidating the processes that connect the growth of planets and stars in a broader cosmic context. The findings from CHAR 1107-7626 not only expand knowledge of rogue planets, but also encourage the development of new theoretical frameworks for understanding mass accumulation and growth in isolated objects. As telescopes like JWST and VLT continue to probe the depths of star-forming regions in the galaxy at large, scientists anticipate that further observations will reveal additional rogue planets exhibiting similar bursts, allowing for comparative studies that refine models of planetary formation, accretion physics, and environmental influence. Each observation contributes to a more comprehensive understanding of the mechanisms driving the evolution of matter in the universe, bridging the conceptual gap between planetary and stellar development, and providing critical insight into the fundamental processes that shape celestial bodies. The remarkable characteristics of CHAR 1107-7626, including its rapid and variable accretion, provide a window into the early and dynamic processes that govern planetary mass objects. These insights offer opportunities to explore how isolated planets interact with their environment, how episodic bursts influence growth, and how similar mechanisms may operate in stars and other massive objects. By studying the interplay between accretion dynamics, environmental conditions, and planetary mass, astronomers are developing a more integrated picture of the continuum of celestial formation processes, revealing connections that were previously overlooked. The research team hopes that continued observations and analysis of CHAR 1107-7626 and other rogue planets will clarify the extent to which accretion bursts are a universal feature of planetary mass objects, and whether such events play a central role in shaping their long-term evolution. By comparing these isolated worlds to both stars and planets within conventional systems, scientists can explore fundamental questions about growth mechanisms, mass accumulation, and the conditions necessary for the formation of stable, isolated celestial bodies. Through detailed study of accretion behavior and environmental interaction, astronomers are gradually unraveling the mysteries of rogue planets and their place within the broader framework of cosmic evolution. The universe is full of mysteries, but among its most puzzling are the origins and growth of supermassive black holes, enormous objects that contain millions or even billions of times the mass of our Sun and are found at the centers of nearly every galaxy. For decades, astronomers have been aware of these cosmic giants, and they have long wondered how such massive objects could form so quickly in the early universe. The discovery of a peculiar object by the James Webb Space Telescope known as QSO-1 may provide an important clue to this enduring mystery. This object existed when the universe was only about 700 million years old, a fraction of its current age of almost 14 billion years. It is extraordinary not just because of its size, but because of its unusual environment and the way it challenges previous ideas about how black holes form and evolve. Supermassive black holes are not ordinary black holes. While typical black holes form from the collapse of massive stars and usually weigh a few times to a few tens of times the mass of the Sun, supermassive black holes are far larger. They can contain hundreds of millions or even billions of solar masses, and their presence in the earliest galaxies has posed a deep puzzle for astronomers. In the early universe, there was relatively little time for these black holes to form and grow, yet observations show that they were already enormous only a few 100 million years after the Big Bang. The standard models of black hole growth, which involve a slow accumulation of gas and mergers with other black holes over billions of years, struggle to explain how such massive objects could appear so early. This tension between observation and theory has driven much of the recent research into early cosmic structures. QSO-1 stands out because it is located in the galaxy cluster Abell 2744, also known as Pandora's cluster. Galaxy clusters are massive structures containing hundreds or even thousands of galaxies bound together by gravity, and their combined mass can bend and magnify light from objects behind them in a phenomenon known as gravitational lensing. This effect is crucial for studying distant objects like QSO-1, because the lensing can make faint and faraway sources appear brighter, and sometimes in multiple locations. Without this cosmic magnification, QSO-1 might have been too faint to detect, and its unusual properties could have gone unnoticed. The light we see from QS01 today began its journey when the universe was only 700 million years old, providing a direct window into a time when the first galaxies and black holes were forming. One of the most striking aspects of QS01 is that it does not appear to be embedded in a fully formed galaxy. Follow-up studies, including research led by Ignas Georgibalis at the University of Cambridge, confirmed the object's extraordinary mass, but also revealed that it lacks a significant component of stars and gas, the elements that normally make up galaxies. In typical supermassive black holes, such as Sagittarius A at the centre of our Milky Way galaxy, the mass of the black hole is only a tiny fraction of the galaxy's total mass. The surrounding galaxy contains billions of stars and vast clouds of gas and dust, dwarfing the black hole itself. In QS01, however, the situation is reversed. The black hole's mass is roughly twice that of the surrounding matter, suggesting that it dominates the system almost entirely. Marta Volonteri, a professor at the Paris Institute of Astrophysics, described QS01 as a very odd system, emphasizing that if more objects like it exist, our understanding of black hole formation could become increasingly complicated. Volonteri, who is a world-leading expert on the formation of supermassive black holes, verified the results independently and found very little room for additional mass beyond that of the black hole itself. This implies that QS01 may represent a new class of early universe objects, where the black hole forms before the galaxy that is normally expected to surround it. The implications of such a discovery are profound. Traditional theories of supermassive black hole formation involve either the collapse of massive gas clouds into a black hole seed, or the growth of smaller black holes from the remnants of the first generation of stars, known as population 3 stars. In both cases, the black hole usually grows within a host galaxy, pulling in gas and occasionally merging with other black holes over millions or billions of years. The discovery of an object like QS01, where the black hole seems to have formed first and the surrounding galaxy is either missing or extremely underdeveloped, challenges these models. It suggests that there may be alternative pathways for creating supermassive black holes in the early universe, perhaps involving direct collapse scenarios in which a black hole forms quickly from a massive unstable gas cloud without first forming a galaxy. Understanding these processes could shed light on how some of the most massive and earliest cosmic structures came to be. The study of QS01 also highlights the remarkable capabilities of the James Webb Space Telescope. Unlike previous instruments, JWST is designed to observe in infrared light, which allows it to detect the faint glow of objects from the earlier stages of the universe. Its sensitivity and precision make it possible to study distant black holes and galaxies that would otherwise remain invisible. In the case of QS01, JWST was able to resolve details about the object's mass and environment that are critical for understanding its nature. Observations like these represent a new era in the study of the early universe, where astronomers can begin to identify and analyze objects that challenge long-standing theoretical models. Gravitational lensing plays a key role in this discovery. The galaxy cluster Abell 2744 serves as a natural cosmic telescope, magnifying the light from QS01 and making it possible to measure its properties in detail. This technique has been used in other studies of distant galaxies and quasars, but the combination of JWST's sensitivity and the lensing effect allowed for an unprecedented look at an object from such an early epoch. By carefully modelling the lensing effects, astronomers were able to confirm the black hole's mass and determine that the system contains very little other matter, reinforcing the conclusion that QS01 is dominated by a solitary supermassive black hole. The fact that QS01 exists at a time when the universe was only 700 million years old raises additional questions about the speed of black hole formation. For a black hole to reach such a mass so early, it must have either formed from an unusually massive initial seed or grown extraordinarily quickly through the accretion of matter. In either case, the efficiency and rapidity of growth required are difficult to reconcile with previous models. Some researchers have suggested that special conditions in the early universe, such as regions of extremely dense gas or unique patterns of cosmic structure, could have facilitated this rapid growth. Others propose that a class of direct collapse black holes could form without a typical stellar progenitor, creating supermassive objects almost immediately. QS01 may be a tangible example of one of these processes, providing a rare observational anchor for theoretical models. Marta Volonteri emphasized the unusual nature of QS01, noting that the system is unlike any other known supermassive black hole at such an early stage. Her independent verification of the mass estimate reinforces the credibility of the findings, suggesting that this is not an observational artifact but a real and extraordinary cosmic structure. If more objects like QS01 are found, it could indicate that supermassive black holes sometimes form before their host galaxies, turning our current understanding of cosmic evolution on its head. Such discoveries could also help explain why supermassive black holes are present in a wide variety of galaxies, including those that seem relatively small or young by cosmic standards. The study of QS01 is also a reminder of the interplay between observation and theory in modern astronomy. For decades, astronomers have relied on theoretical models to predict how supermassive black holes form and evolve, but observations like these force a re-evaluation of assumptions. The presence of a black hole dominating a system without a corresponding galaxy component suggests that the early universe may have been more diverse and complex than previously imagined. This diversity may reflect variations in local conditions, such as the density and temperature of gas clouds, the presence of dark matter, or interactions with nearby structures. Each new observation provides an opportunity to refine models and explore the range of possible pathways that lead to the formation of the universe's most massive objects. In addition to the mass of the black hole itself, the absence of surrounding stars and gas in QS01 has implications for understanding galaxy formation in the early universe. Normally, galaxies grow alongside their central black holes, with feedback from the black hole regulating star formation and the distribution of gas. In QS01, however, the black hole appears to have achieved a large mass before substantial galaxy formation occurred, suggesting that early black hole growth can proceed independently of the typical galactic environment. This raises questions about the timing and mechanisms of galaxy assembly, as well as the role of black holes in shaping their host systems over cosmic time. The discovery of QS01 also highlights the importance of follow-up studies in confirming unusual observations. Initial detections may suggest a surprising or anomalous object, but careful analysis is required to verify mass estimates and rule out alternative explanations. In this case, the work led by Ignace George-Barlis, combined with independent verification by Marta Voluntari, strengthens confidence in the conclusion that QS01 is dominated by a supermassive black hole with minimal surrounding matter. This rigorous approach is essential in advancing our understanding of the early universe, where rare and extreme objects can challenge existing theories and prompt new avenues of research. The existence of QS01 underscores the remarkable pace of discovery in modern astrophysics. In just a few decades, astronomers have gone from the first detection of supermassive black holes to detailed studies of their growth and environment in the early universe. Instruments like the James Webb Space Telescope, combined with natural gravitational lenses, allow researchers to probe regions of space and time that were previously inaccessible. Each new observation adds to a growing picture of cosmic evolution, revealing both expected patterns and surprising anomalies that push the boundaries of knowledge. Supermassive black holes like QS01 also provide a window into the conditions of the early universe. The mass and growth rate of these objects reflect the availability of gas, the density of surrounding matter, and the dynamics of cosmic structure formation. By studying objects that formed only hundreds of millions of years after the Big Bang, astronomers can infer the physical processes that governed the earliest epochs of galaxy and black hole formation. These insights help to explain not only the presence of supermassive black holes in the distant universe, but also their influence on the development of galaxies over billions of years. The peculiar nature of QS01, with its massive black hole and lack of a substantial host galaxy, raises the possibility that other such objects may exist. If additional systems are found, they could represent a distinct population of early black holes that formed through rapid or unusual pathways. Identifying and characterizing these objects will require further observations with JWST and other powerful telescopes, as well as detailed modeling to understand the underlying physics. The discovery of QS01 may thus mark the beginning of a new chapter in the study of black hole formation, where astronomers explore a wider range of scenarios and refine theoretical frameworks to accommodate unexpected findings. In the context of cosmic history, QS01 provides a rare glimpse into a time when the universe was still in its infancy. At only 700 million years old, the universe was in the process of forming the first generations of galaxies and stars. The presence of a massive black hole at this stage suggests that some regions of space experienced accelerated growth or unique conditions that allowed such rapid accumulation of mass. Studying QSO-1 and similar objects helps to illuminate the early stages of structure formation, providing clues about how the first galaxies and black holes emerged from the primordial universe. The contrast between QSO-1 and Sagittarius A, the black hole at the centre of the Milky Way, is striking. While Sagittarius A has a mass of only a few million times that of the Sun, it sits within a galaxy containing hundreds of billions of stars and vast amounts of gas and dust. In QSO-1, the black hole's mass is greater than the total mass of surrounding matter, highlighting the unusual nature of this early universe system. This comparison underscores the diversity of black hole environments and the potential for extreme variations in the timing and mechanisms of growth. Understanding these differences is key to developing a comprehensive picture of black hole formation across cosmic history. The observations of QSO-1 also demonstrate the synergy between advanced technology and natural phenomena in astronomy. JWST provides the sensitivity and resolution needed to detect faint, distant objects, while gravitational lensing magnifies and clarifies these sources. Together, these tools allow astronomers to study the earliest supermassive black holes in unprecedented detail. The success of this approach suggests that future surveys and observations may uncover more unusual systems, expanding our understanding of the diversity of early cosmic structures and challenging existing models. The discovery of QSO-1 has inspired a re-evaluation of long-standing assumptions about the relationship between black holes and galaxies. Traditionally, black holes were thought to grow alongside their host galaxies, with feedback mechanisms regulating star formation and gas accretion. In QSO-1, however, the black hole appears to have grown independently, dominating a system with very little other matter. This observation suggests that alternative pathways for black hole formation and growth may exist, particularly in the early universe. Identifying these pathways and understanding their prevalence will be an important goal for future research. The study of QSO-1 also highlights the importance of international collaboration in modern astronomy. Researchers from multiple institutions, including the University of Cambridge and the Paris Institute of Astrophysics, contributed to the analysis and interpretation of the data. This collaborative approach combines observational expertise, theoretical modelling, and computational analysis, allowing for a more comprehensive understanding of unusual cosmic objects. The findings from QSO-1 demonstrate the value of such collaborations in addressing complex questions about the origins and evolution of supermassive black holes. The implications of QSO-1 extend beyond black hole formation to broader questions about the evolution of galaxies and cosmic structures. The existence of a massive black hole without a substantial host galaxy challenges the idea that galaxies and black holes always grow together. It suggests that in some regions of the early universe, black holes may have formed first, influencing subsequent galaxy formation in ways that are not yet fully understood. Studying these systems provides insights into the interplay between black holes, gas, stars, and dark matter, and helps to refine models of cosmic evolution. QSO-1 also serves as a benchmark for testing theoretical predictions about black hole growth. The object's mass, age, and environment provide concrete data points that can be used to evaluate different formation scenarios, such as direct collapse models or rapid accretion of matter. By comparing observations with simulations and theoretical models, astronomers can better understand the conditions that lead to the formation of supermassive black holes in the early universe. This iterative process of observation and modelling is central to advancing knowledge in astrophysics and resolving long-standing mysteries. The discovery of QSO-1 raises intriguing possibilities for the population of supermassive black holes in the early universe. If objects like QSO-1 are not unique, they may represent a class of early black holes that formed under extreme or unusual conditions. Identifying additional members of this population will require careful observations and may reveal a diverse range of black hole growth pathways. Such studies could transform our understanding of the early universe, revealing a complex landscape of cosmic structures and shedding light on the processes that shaped the first billion years of cosmic history. The unusual characteristics of QSO-1, including its massive black hole and minimal surrounding matter, highlight the dynamic and varied nature of the universe. They demonstrate that even in the earliest epochs, cosmic evolution was not uniform, with some regions experiencing accelerated growth or unique conditions that led to the formation of extreme objects. Observing and understanding these anomalies is essential for building a complete picture of the universe's history, from the first stars and galaxies to the complex structures we see today. The case of QS01 emphasizes the importance of detailed measurements and careful analysis in astrophysics. Determining the mass of the black hole, assessing the presence of surrounding gas and stars, and modeling the effects of gravitational lensing all require precise observations and sophisticated computational techniques. These efforts enable astronomers to identify unusual systems and to explore their implications for broader questions about the universe. In QS01, the combination of advanced telescope technology, natural gravitational lenses, and rigorous analysis has revealed an object that challenges conventional wisdom and opens new avenues for research. QS01 also underscores the need to explore the early universe in multiple wavelengths of light. Infrared observations like those provided by JWST are particularly valuable for studying distant objects whose light has been stretched to longer wavelengths by the expansion of the universe. By observing in infrared, astronomers can detect faint signals from the earliest black holes and galaxies, gaining insight into their composition, growth, and environment. These observations complement studies at other wavelengths, providing a more complete understanding of cosmic history. The discovery of QS01 represents a remarkable step forward in the study of supermassive black holes and the early universe. Its massive black hole, lack of surrounding matter, and early formation provide a unique window into a period when cosmic structures were first emerging. By studying objects like QS01, astronomers can investigate alternative pathways for black hole formation, explore the relationship between black holes and galaxies, and refine models of cosmic evolution. Each new observation adds to our knowledge of the universe, revealing both the expected and the extraordinary in the vast expanse of space. The contrast between QS01 and other known black holes highlights the diversity of cosmic systems. While many supermassive black holes reside in fully formed galaxies, QS01 challenges this paradigm, suggesting that black holes can dominate systems independently of galactic structures. This diversity underscores the complexity of the early universe and the range of processes that can lead to the formation of massive objects. Studying these differences provides insight into the physical mechanisms that govern black hole growth and the evolution of galaxies over billions of years. QS01 also illustrates the power of modern astronomical tools and methods. JWST's infrared capabilities, combined with the natural magnification provided by gravitational lensing, enable the detection and analysis of objects that were previously inaccessible. These observations push the boundaries of our understanding, revealing systems that challenge existing theories and prompting new questions about the nature of the universe. The ability to study such distant and unusual objects marks a significant advance in observational cosmology. The discovery of QS01 encourages astronomers to consider a wider range of possibilities for early black hole formation. It suggests that under certain conditions, supermassive black holes can form and grow rapidly, potentially preceding the formation of their host galaxies. This challenges traditional models and opens the door to new theoretical scenarios, including direct collapse mechanisms and accelerated growth processes. Investigating these possibilities requires continued observations, advanced simulations, and careful analysis of both existing and newly discovered objects. The study of QS01 also emphasizes the interplay between theory and observation in advancing astrophysics. Observations provide empirical data that test theoretical predictions, while models help interpret the meaning of those observations and guide future research. In the case of QS01, the unusual characteristics of the object provide a critical test for models of black hole growth and early galaxy formation. By examining such systems, astronomers can refine their understanding of the conditions that lead to the emergence of the universe's most massive objects. The mass and dominance of QS01's black hole also offer insights into the potential influence of early supermassive black holes on their surroundings. Even in the absence of a fully formed galaxy, a black hole of this size could have significant effects on nearby gas, star formation, and the evolution of other structures in its vicinity. Understanding these interactions helps to build a more complete picture of the early universe, including the feedback processes that shape the development of galaxies and cosmic structures over time. As the James Webb Space Telescope began gathering its earliest sets of data in the year 2022, astronomers suddenly found themselves confronted with something they did not expect. spread across the deep sky, hidden in some of the earliest chapters of cosmic history, were numerous compact and strangely red-coloured objects that researchers quickly began calling little red dots. These faint but intense points of light appeared at times ranging from roughly 500 million years after the Big Bang to about 1,500,000,000 years after the universe came into being. Even without any detailed explanation for them, these tiny systems immediately hinted at something astonishing. Galaxies, black holes, or perhaps both were forming earlier, faster, and in more extreme ways than astronomers had believed for decades. The little red dots seemed to challenge almost every established idea about how the universe grew in its youth. Many of them were unusually bright, extremely red, and compact in size. Their colours suggested that their light had travelled through enormous stretches of expanding space, which also meant they must have formed when the universe was still overwhelmingly young. Their intensity suggested powerful processes happening inside them, possibly involving early supermassive black holes or young, incredibly hot stars. Yet their shapes and sizes were so small that they appeared unlike the more familiar galaxies we see around us today. Even as these strange objects continued to puzzle astronomers, another discovery emerged that added even more complexity to the growing mystery. A peculiar object known as QSO-1 was spotted in the massive galaxy cluster Abell 2744, also called Pandora's cluster. The immense mass of the cluster acted like a giant natural lens, bending and magnifying ancient light that had travelled across almost the entire lifetime of the cosmos. Because of this gravitational lensing effect, the light from QSO-1 appeared brighter and clearer than it otherwise would have. The light detected from it had begun its journey when the universe was only about 700 million years old, at a time when galaxies were just beginning to assemble and when stars were still in some of their earliest generations. By comparison, the universe today is almost 14 billion years old. Astronomers had long known that supermassive black holes existed in the modern universe. They sit in the centres of most large galaxies, including our own Milky Way, where the central black hole is known as Sagittarius A star. But for many years, researchers found themselves struggling to understand how such gigantic black holes could have formed so quickly in the universe's youth. Some of the earliest quasars discovered in the distant cosmos appear to host black holes billions of times more massive than the Sun, even though they existed less than 1 billion years after the Big Bang. How such enormous objects formed so early had remained a major puzzle. The discovery of QSO-1 offered something new, a different kind of ancient object, one that did not seem to follow the usual blueprint of early galaxy formation. The first detailed analysis of QSO-1 was carried out in February of the year 2024. It revealed that the system contained a black hole with a mass of about 50 million times the mass of the Sun. While this was not as massive as the most extreme early quasars known, it was still astonishingly large for something so ancient. What made QSO-1 even stranger was not simply its mass, but what appeared to be missing around it. The system seemed to have only a small amount of gas and very few stars. Instead of being a normal galaxy with a central black hole, QSO-1 looked more like a black hole dominating an almost empty environment. A recent follow-up study led by Ignas Georgibalis from the University of Cambridge confirmed both the enormous mass of the black hole and the unusual absence of surrounding matter. The researchers showed clearly that QSO-1 lacked any significant population of stars or large reservoirs of gas. There was no bright galaxy wrapped around its black hole. There was no obvious structure that matched the kinds of early galaxies astronomers had expected to find from that cosmic era. Almost the entire mass of the system seemed to come from the black hole itself. Marta Volonteri, a leading expert on the formation of supermassive black holes at the Paris Institute of Astrophysics, described the system as exceptionally odd. She double-checked the observations using her own methods and concluded that there was extremely little room for any additional mass besides the black hole. In QSO-1, the black hole appeared to be about twice as massive as all the surrounding gas and stars put together. This is the exact opposite of what is seen in galaxies like the Milky Way, where the central black hole represents only a tiny fraction of the galaxy's total mass. The existence of QSO-1 suggested that at least some early black holes grew extremely rapidly, even before their host galaxies had time to build up large amounts of stars or gas. This raised a major question. How could a black hole form first before the surrounding galaxy? And if it did, what kind of process could have created such an object? As researchers continued studying QS01, they began to connect it with the earlier discovery of the little red dots. Many of these compact and red systems also seemed to harbour black holes that were unexpectedly large for their age. They hinted that the growth of black holes might have started earlier than the formation of most galaxies. The little red dots, far from being rare or isolated objects, appeared numerous in the early universe. Their presence suggested that rapid black hole growth may have been a common process, not an unusual exception. Classical astrophysics describes black holes as forming when massive stars collapse at the end of their lives. After exhausting their nuclear fuel, these stars can no longer resist their own gravity and collapse inward, producing a black hole that is typically a few times to a few dozen times more massive than the Sun. Over time, these black holes can grow by feeding on gas clouds, merging with other black holes or consuming nearby stars. But these growth processes take time, often hundreds of millions or billions of years. So how could black holes grow to millions or billions of times the Sun's mass in less than a billion years after the Big Bang? One idea suggests that instead of starting small, some of the earliest black holes may have formed from the direct collapse of massive gas clouds. These direct collapse black holes could have started with masses thousands or even hundreds of thousands of times the mass of the Sun, making their growth into supermassive sizes far easier. This idea gained strong support with the discovery of a system known as UHZ-1, which displayed classic signs of having formed through direct collapse. A team led by Priyamvada Natarajan at Yale University reported that UHZ-1's characteristics matched theoretical predictions for such early massive black holes. But QS01 seemed to be different. It did not fit easily into the direct collapse model. Instead, as Voluntary explained, some members of the research team suggested that QS01 could have formed from something even more exotic, a primordial black hole, or perhaps a form of dark matter collapsing due to the way it interacts with itself. In either scenario, the black hole would have existed before any normal matter, like gas or stars, had gathered around it. The concept of primordial black holes is not new. In the year 1967, the Soviet physicists Yakov Zeldovich and Igor Novikov proposed that in the earliest fractions of a second after the Big Bang, some regions of the universe might have contained such extreme densities of matter that they collapsed into black holes before the first atoms even formed. A few years later, in the year 1971, the physicist Stephen Hawking expanded on the idea and demonstrated that primordial black holes could come in a wide range of sizes. Over the decades, many astrophysicists have investigated these ideas, exploring whether primordial black holes could explain dark matter, early cosmic structure, or unusual astronomical observations. If QS01 is indeed a primordial black hole, then it would mean that the black hole started forming almost immediately after the universe began. It would have had an enormous head start compared with black holes formed from stars, which only appear after stars themselves are born. In such a scenario, QS01 would have begun growing long before the surrounding galaxy had formed. This could explain why the black hole appears so large while the galaxy itself remains faint and underdeveloped. Voluntary pointed out that the black hole in QS01 appears to have grown a great deal without triggering any significant star formation. Usually, when gas falls into a forming galaxy or a growing black hole, it becomes heated, turbulent, or compressed, often leading to the birth of new stars. But in QS01, the gas did not appear to have formed many stars at all. Instead, almost every visible piece of matter in the system seemed to end up in the black hole or became part of its gravitational influence. This behaviour suggested a very different kind of cosmic evolution, one in which the black hole grew far faster than its galaxy. The little red dots added to this mystery by revealing many similar cases scattered across the deep sky. More than a dozen detailed studies of these compact systems suggested that they often contained black holes that were surprisingly massive for their early ages. Instead of being small seed black holes expected from the collapse of early stars, many of these black holes appeared already grown to millions of solar masses, and yet the galaxies around them remained small, faint, or incomplete. Some little red dots showed signs of intense activity, likely driven by black holes consuming matter at high rates. Others appeared more stable but still unusually massive relative to their size. The large number of these objects suggested that the early universe may have hosted a wide population of fast-growing black holes, potentially formed through different processes than the ones that operate today. The discovery also affected the long-standing question of which forms first in galaxy evolution, the galaxy or the black hole. Classical models assume that galaxies form first, gathering large amounts of gas and forming stars. Eventually, some of these stars die and collapse into black holes. Over time, these black holes grow and eventually become supermassive. But if objects like QSO-1 are common in the early universe, this order of events may need to be reversed or at least reconsidered. In many early systems, the black hole may have formed before the galaxy, acting as a seed around which the galaxy later developed. In some cases, the black hole may have even shaped how the galaxy grew. Because QSO-1 lies in the same era as many little red dots, it hints that early black holes may have played a more important role in shaping the universe than previously believed. Astronomers had long assumed that black holes were products of galaxies, not their drivers. But the new evidence suggests that black holes may have acted as anchors, gravitational centers around which early galaxies assembled. In this view, the earliest galaxies might not have been well-formed spiral or elliptical systems, but rather loose gatherings of matter slowly shaped by the gravitational pull of central black holes that were already growing. Meanwhile, the gravitational lensing in Abell 2744 allowed astronomers to study QSO-1 in greater detail. The lensing effect stretched and magnified the light from behind the cluster, revealing that QSO-1 appeared in multiple images, each distorted by the mass distribution of the cluster. This provided additional confirmation that the central object was extremely small in physical size, yet extremely bright and massive. Such details helped rule out alternative explanations, such as the possibility that QSO-1 was simply a compact dwarf galaxy with a normal black hole. As researchers studied the spectral fingerprints of the light from QSO-1, they found that the surrounding gas moved at extremely high speeds, consistent with the presence of a very large black hole. Yet the amount of gas was surprisingly limited. If this black hole had been forming in a typical early galaxy, there should have been far more gas fueling both star formation and black hole growth. But QSO-1 showed almost none of those signs. Instead, it behaved like an object that had grown in isolation or under unusual conditions. The detection of numerous little red dots strengthened the idea that early black holes might have been forming long before astronomers once thought. These dots appeared extremely compact, often only a few hundred light-years in size, far smaller than modern galaxies. Yet they were bright, intense, and often dominated by red light shifted to longer wavelengths by the universe's expansion. Their abundance suggested that fast-growing black holes were widespread in the early universe. Some little red dots showed evidence of extremely hot dust surrounding the black holes, possibly created as matter heated up while spiraling into them. Others showed spectral signs that suggested the presence of highly ionized gas, another symptom of powerful black hole activity. In several cases, the black holes inside these dots seemed too large relative to the tiny size of the host galaxy. Normally, galaxies grow first and black holes grow slowly within them, but here the black holes seemed to be taking the lead. These discoveries pointed toward a universe that evolved faster and more energetically than earlier models predicted. Instead of forming slowly over long periods of time, many early cosmic structures seem to have grown explosively, driven by intense gravitational forces and rapid accumulation of matter. The presence of early black holes also affected the surrounding gas, potentially shaping the formation of stars and the development of early galaxies. As astronomers continued studying these phenomena, they asked whether QSO-1 and the little red dots belonged to the same class of objects, or whether they represented different stages of a broader process. Some suggested that QSO-1 might be an extreme example of the little red dot population, an early black hole that had already consumed nearly all available matter, leaving behind only a faint underdeveloped galaxy. Others suggested QSO-1 might be something even more exotic, perhaps a primordial black hole or a new category of early cosmic object. As the debate grew, more data from the James Webb Space Telescope continued to provide new clues. Observations of faint and distant systems revealed unexpected brightness, unusual colours, strange shapes, and rapid evolution. New spectral data suggested that some little red dots contained elements forged in earlier generations of stars, indicating that they hosted complex chemical processes even at young cosmic ages. Others were so compact and bright that they resembled quasars, but with much smaller host galaxies. Yet many key questions remained. What forces caused these early black holes to grow so quickly? Why did some form before galaxies? How common were they? Did primordial black holes truly exist? And if so, how large were they? And what role did they play in shaping the early universe? The system QSO-1 with its dominant black hole and faint surrounding matter, represented a crucial piece of this puzzle. It showed that some black holes had grown far beyond expectations in the universe's first few 100 million years. It demonstrated that galaxies did not always form first. It revealed that black holes could exist without large stellar populations, and it confirmed that the early universe may have been a far more dynamic and energetic environment than previously believed. The discovery of little red dots deepened this mystery even further. These compact objects scattered across the sky suggested that rapid black hole growth was not a rare phenomenon. Instead, it may have been a key driving force in early cosmic evolution. Many of these dots showed signs of intense gravitational activity, hot dust, gas flows, or energetic processes associated with black holes. As researchers studied them, they found that the sizes, colours, and brightness of little red dots varied greatly. Some were extremely red, suggesting large distances or heavy dust obscuration. Others were less red but still compact and bright. Their variety suggested different evolutionary paths, different kinds of black holes, or different environmental conditions. While some little red dots might have formed through direct collapse of gas, others might have grown from the remnants of the first stars. Still others might have begun as primordial black holes, formed almost instantly after the Big Bang. Each of these possibilities offered insights into different aspects of cosmic history. Researchers continued analysing QS01 and the little red dots, using every available instrument to measure their properties. They studied the motion of gas, the distribution of light, the spectral signatures of elements, and the gravitational effects of massive objects. They compared observations with detailed theoretical models that described how early black holes could grow, how gas could collapse, and how galaxies could form around massive centres. These studies helped refine the timeline of early cosmic history. They showed that black holes could grow rapidly when fed by dense gas streams or during periods of gravitational instability. They revealed that some black holes might have fed at rates close to the maximum allowed by physics. They suggested that early gas-rich environments could help black holes grow much faster than they do in the modern universe. Yet QS01 remained unusual. Its unusually low amount of gas and stars meant that its black hole had somehow grown without creating a large galaxy. This raised the possibility that some black holes formed in ways that did not require traditional star formation. Perhaps exotic processes, such as the collapse of dark matter structures or early density fluctuations, played a role. Perhaps the earliest parts of the universe had conditions that allowed black holes to form and grow more easily. Researchers also questioned how long objects like QS01 could remain in such a peculiar state. Would its surrounding galaxy grow later, slowly catching up with the black hole? Or would the system remain dominated by its massive black hole indefinitely? Could this object represent a unique moment in cosmic evolution, or a glimpse into a widespread but short-lived stage that most early galaxies passed through? As these questions continued to shape research, the little red dots became an essential component in understanding the universe's earliest chapters. Their discovery showed that compact, powerful, and rapidly evolving objects were common in the early cosmos. Their presence revealed unexpected patterns of early growth, unusual pathways of galaxy formation, and surprising forms of black hole evolution. Together, QS01 and the little red dots helped transform the way astronomers understood the earliest billion years of cosmic history. They showed that the universe's first structures were not simple or predictable. Instead, they were dynamic, varied, and sometimes extreme. They demonstrated that black holes played a major role in shaping the early cosmos. They offered evidence that galaxies formed in ways far more complex and diverse than classical models suggested. In the early universe, which came first, the galaxy or the black hole? And perhaps with objects like QS01 leading the way, the universe is slowly beginning to provide an answer. The James Webb Space Telescope, with its giant honeycomb mirror made of golden hexagons and its eyes tuned to catch the faintest glow of infrared light, has turned its gaze toward one of the most energetic and dramatic galaxies in our cosmic neighbourhood. When its instruments looked at this galaxy, they revealed a bright, blazing heart where new stars are being born at an unbelievably fast pace, and powerful winds flowing out of the centre carry dust and gas far into space. This galaxy is known as Messier 82, sometimes called NGC 3034, the Cigar Galaxy, or simply M82, and it sits roughly 12 million light-years from Earth, resting quietly in the northern constellation that people have called Ursa Major for many centuries. Even though it appears peaceful from far away, this galaxy is one of the most dramatic star-forming regions in our part of the universe. Messier 82 belongs to what astronomers call a starburst galaxy, which means it is forming stars at an extremely intense speed, much faster than large normal galaxies such as our own Milky Way. If the Milky Way makes stars at a slow and steady pace, almost like calm raindrops falling from the sky, Messier 82 is more like an enormous cosmic storm filled with lightning and thunder as new stars burst into life. This galaxy is the second largest member of a group of galaxies known as the M81 group, named after its massive spiral neighbour Messier 81, which lies nearby. It has what astronomers call a D25 isophotral diameter of a little more than 12.52 kiloparsecs, which means the disk of visible light spreads across about 40,800 light-years. All of these numbers become far more astonishing when compared with our Milky Way, because M82 shines with about 5 times the total brightness of our galaxy, and its central region, where the starburst is happening, glows about 100 times brighter. It is almost overwhelming to imagine so many stars, clouds, bursts of radiation, and powerful winds packed into the inner part of a galaxy not too far from ours. Scientists think that the reason M82 suddenly turned into such an active star-forming beast is because it had a close encounter with its neighbour M81 in the recent past. This interaction between galaxies is not violent in the sense of collisions, but their gravitational pull can stretch, twist, and disturb each other. When this happens, gas can be pulled, squeezed, or pushed inward toward the centre, where it becomes dense enough to collapse and form new stars. In the case of M82, the gravitational handshake with M81 seems to have stirred up so much gas that the galaxy has been firing out new stars like fireworks for millions of years. Because this galaxy is near enough to Earth, it has become the textbook or prototypical example of a starburst galaxy, a nearby laboratory that astronomers can study in great detail to understand how these intense periods of star formation work. In the month of January in the year 2014, a bright explosion inside this galaxy caught the attention of astronomers all around the world. This was a Type Ia supernova known as SN 2014J, discovered on the 21st day of January in the year 2014. A Type Ia supernova happens when a white dwarf star, which is the leftover core of a dead star, becomes unstable because it steals too much material from a companion star or merges with another white dwarf. Then it suddenly explodes in a brilliant flash that can outshine an entire galaxy. This explosion gave scientists a chance to observe one of these rare events almost in our cosmic backyard. Later in that same year, astronomers studying M82 also discovered the brightest pulsar ever detected at that time. This object was labelled M82X2, and it showed bursts of X-ray light that signalled the presence of a spinning neutron star with incredible energy, the brightest example known then. Nearly 10 years later, in the month of November, in the year 2023, another astonishing event unfolded inside the same galaxy. This time, astronomers detected a blast of gamma rays, the most energetic kind of radiation known in the universe. When they studied it carefully, they realized it came from a magnetar, which is a special kind of neutron star with an extraordinarily powerful magnetic field. This was historic because it was the very first time that this kind of gamma ray burst caused by a magnetar was detected outside the Milky Way. Before this moment, scientists had only found 3 such bursts within our galaxy, making this the 4th one ever detected anywhere. For such a small galaxy in our local neighbourhood, M82 certainly does not hesitate to put on dramatic cosmic shows. Messier 82 has not been unknown to astronomers for long. It was first recorded in the year 1774 by Johann Elert Bode, a German astronomer who described it as a faint cloudy spot in the sky. He mentioned that it sat about 3/4 of a degree away from the neighbouring galaxy M81 and looked elongated and pale. A few years later, in the year 1779, the astronomer Pierre Méchain rediscovered these 2 objects independently and sent the information to Charles Messier. Messier, who was creating a catalogue of fuzzy objects in the sky so that others would not confuse them with comets, added both of these galaxies to his famous list, and so the galaxy we now call the Cigar Galaxy became number 82 in Messier's catalogue. For a long time, astronomers believed that M82 was a simple irregular galaxy, meaning it did not have the clear structure of spirals or ellipses. However, in the year 2005, a surprising discovery changed this idea completely. Using near-infrared images, scientists noticed two symmetric spiral arms hidden inside the galaxy. These spiral arms had been masked from view because the galaxy's disk is almost edge-on from our point of observation, tilted by roughly 80 degrees. The disk is also filled with thick clouds of dust that absorb visible light, making it hard to see through. By subtracting what they expected from a smooth, evenly lit disk, astronomers uncovered the faint patterns of these arms. Even though the arms were detected in infrared light, they were actually bluer than the main disk when looked at in other wavelengths, which meant they were different in composition or temperature. These arms stretch outward from the ends of a structure known as a bar in the center of the galaxy, and can be traced for about 3 times the scale of the main disk. Assuming that the upper side of the galaxy is closer to us, as most astronomers do, the spiral arms appear to be trailing behind the direction of the galaxy's rotation. The Hubble Space Telescope also revealed just how active and crowded the center of the galaxy truly is. In that same year, 2005, Hubble spotted 197 young massive clusters tightly packed inside the galaxy's core. These clusters are groups of newborn stars gathered so close together that they shine like bright knots of light. Each cluster has an average mass of about 200,000 times the mass of our Sun. This means the central region of M82 is one of the densest star-forming environments known, a chaotic place where clouds of gas collapse into stars at a rate 10 times faster than the total rate of star formation inside the entire Milky Way galaxy. Every direction around this core is filled with glowing dust, hot gas, bright clusters, and shock waves from supernova explosions. The heart of the galaxy, where the starburst is happening, spans a region about 500 parsecs across. Inside this zone, astronomers have identified 4 especially bright knots of activity known as clumps A, C, D, and E. These clumps are visible not only in ordinary light but also in X-rays, infrared, and radio waves. Because they show up so clearly in many different kinds of observations, scientists believe these 4 regions are among the least obscured star-forming clusters in the entire galaxy when viewed from Earth. 2 of the clumps, A and C, appear to be the main sources of the galaxy's powerful bipolar outflow, also called the superwind. This superwind is a dramatic blast of gas flowing out of the galaxy's center in 2 opposite directions, like smoke being pushed out of a chimney. The energy driving this superwind comes from countless supernova explosions that occur inside the core, roughly 1 explosion every 10 years. These explosions heat and push gas outward, carving huge lanes of glowing material that stretch far above and below the main disk. Observations made with the Chandra X-ray Observatory added yet another surprising chapter to the story of this extraordinary galaxy. About 600 light-years from the center of M82, astronomers detected X-ray emissions that were flickering or fluctuating unpredictably. The best explanation for this strange behavior is that the emissions come from what might be the first known intermediate mass black hole, with a mass somewhere between 200 and 5,000 times the mass of the Sun. This type of black hole is something scientists have searched for over many decades but rarely found, because most known black holes are either small, a few times the mass of the Sun, or supermassive, millions of times heavier. To have one that falls in between, an intermediate range, is exciting and unusual. M82 also houses a supermassive black hole at its very center, just like most galaxies. This one has a mass of about 3 times 10 to the power of 7 solar masses, measured by studying how stars near the center move under the black hole's intense gravitational pull. In the month of April in the year 2010, radio astronomers working at the Jodrell Bank Observatory at the University of Manchester in the United Kingdom discovered something very mysterious inside M82. A strange object had begun to emit radio waves, but the pattern of these waves did not match anything astronomers had ever seen in the universe before. It did not look like a supernova, a pulsar, a black hole jet, or anything familiar. Many theories were suggested, but none fit the strange data perfectly. One idea proposed that it might be an unusual kind of microquasar, a system where a black hole or neutron star produces jets of energy. However, all known microquasars give off large amounts of X-rays, and this object gave off so few that they fell below the measurement limit. Another strange thing was that this object was located several arc-seconds away from the galaxy's center, which meant it was unlikely to be linked to the supermassive black hole at the core. What shocked astronomers most was that the object appeared to move 4 times faster than the speed of light relative to the galaxy's centre, even though this does not break the laws of physics, because apparent superluminal motion can happen when an object's jet moves close to the speed of light at a particular angle. The observation was still extremely unusual and added another puzzle to the already long list of mysteries inside M82. As if this galaxy had not already provided enough surprises, its close relationship with the larger galaxy M81 continues to shape and mould its fate. The gravitational forces between the two galaxies have been interacting for at least 100 million years. This ongoing tug-of-war has distorted the shape of M82 and pulled huge amounts of gas toward its centre. Over the past 200 million years, at least one close encounter funneled a large quantity of gas into the core of M82, sparking a wave of star formation. The most recent encounter, believed to have occurred between 200 million and 500 million years ago, caused a burst of star formation that created an entire generation of star clusters. Scientists think that this burst lasted for up to 50 million years, and during this period, new stars formed at a rate of about 10 solar masses every year. After this main burst, 2 more smaller bursts of star formation happened. The most recent one, which occurred between 4 million and 6 million years ago, likely created many of the massive star clusters that now fill the galaxy's core. The disk of M82 also carries evidence of older waves of star formation. Many stars in the disk appear to have formed in a large burst roughly 500 million years ago. This left the disk filled with hundreds of clusters that resemble globular clusters, except they are younger and still evolving. Star formation in the disk seems to have stopped about 100 million years ago, leaving only the central region and the halo with ongoing activity. Some scientists think that M82 may have once been a low-surface brightness galaxy, meaning it was dim and quiet, until interactions with M81 stirred it awake and forced it into its current starburst phase. From Earth's viewpoint, the centres of M81 and M82 appear to be separated by about 130,000 light-years when ignoring the small difference in their distance from us. The actual separation is believed to be roughly 300,000 light-years, give or take 200,000. As a starburst galaxy filled with young, massive stars, M82 experiences powerful supernovae far more often than calmer galaxies. The first reported supernova candidate inside the galaxy was called SN 1986d, but it turned out to be a false alarm. The object was not a supernova after all, but a variable infrared source. The first confirmed supernova was SN 2004 AM, discovered in the month of March in the year 2004 from images taken in November in the year 2003. Later studies showed it was a Type II supernova, a kind that happens when a massive star collapses at the end of its life. In the year 2008, astronomers detected a strange radio-only transient, which they called SN 2008IZ. It was likely a supernova hidden behind clouds of dust and gas that blocked all visible light. Another similar radio-only transient was detected in the year 2009, but it never received an official name and remained unconfirmed. Supernova explosions likely happened many more times in the decades before modern surveys. In the 1980s and 1990s, astronomers using the European VLBI network studied old supernova remnants inside M82. One of these remnants clearly expanded between the years 1986 and 1997, suggesting that the original supernova occurred in the early 1960s. 2 other remnants may have been almost as young, but their expansion was not firmly confirmed at the time. One of the most exciting moments for amateur and professional astronomers alike came on the 21st day of January in the year 2014 at 19 hours and 20 minutes Universal Time. A new star suddenly appeared in the galaxy, bright enough to be visible through small telescopes. It was discovered by astrophysics lecturer Steve Fossey and 4 of his students at the University of London Observatory. At first it glowed at magnitude 11.7, then brightened to magnitude 10.9 2 days later. Images taken on earlier dates, from the 15th to the 20th of January, showed that it had risen from magnitude 14.4 to 11.3. Observations from the 14th showed nothing down to magnitude 17. Early analysis suggested that it might brighten to magnitude 8.5, becoming visible even through binoculars, but it eventually peaked at magnitude 10.5 at the end of the month. It was classified as a young reddened Type Ia supernova and given the name SN 2014J by the International Astronomical Union. The last Type Ia supernova as close as this one was SN 1972e, making SN 2014J the nearest one of its type in over 4 decades. The James Webb Space Telescope, which continues to operate as one of the most advanced observational tools ever placed in space, captured an image for the Halloween period showing the Red Spider Nebula, a planetary nebula that represents the late evolutionary state of a dying star. This image is not only visually striking, with structures that resemble a spider-like form spreading across space, but also scientifically important because it reveals physical conditions that may occur in our own solar system when the Sun reaches the planetary nebula stage in several billion years. The Red Spider Nebula, also known under the catalogue designation NGC 6537, is found near the dense and complex region close to the central part of the Milky Way galaxy, slightly to the northwest of the constellation that we call Sagittarius. It was first identified by the astronomer Edward Charles Pickering on the 15th day of July in the year 1882, during a period in astronomy when photographic plates were just beginning to reveal deep sky objects invisible to the human eye. The nebula shows a shape with 2 large lobes opposite each other, producing a bipolar structure. This kind of shape is common in many planetary nebulae, but in the case of the Red Spider Nebula, the lobes are unusually pronounced and appear to show a clear S-shaped symmetry, in which each lobe curves in a way that mirrors the other. Astronomers propose that this symmetry could be the result of a binary system at the centre, where the white dwarf remnant of the original star interacts gravitationally with a close companion object. Binary interactions can produce precession, channeled winds and jets that create curved or spiral-like shapes in the ejecta. Another possible cause involves strong magnetic fields carried by the outflowing stellar wind, which could guide the direction of the expelled gas and create the observed structure. However, the gas surrounding the lobes is not smooth or uniform. Instead, high-resolution observations show that the walls of the lobes contain many irregular ripples and unstable patterns, likely caused by complex interactions between fast winds, older layers of material, and regions with different densities. At the core of the nebula is a white dwarf, which is the dense leftover core of the star that produced the nebula. This white dwarf produces an extremely hot stellar wind with a temperature close to 10,000 Kelvin, blowing outward at roughly 300 kilometers per second, which is far faster than winds known from most other stars. A stellar wind of this speed carries enough energy to push on surrounding gas and create shock fronts. These shocks propagate through the nebula and create large wave-like structures. Studies estimate that these waves can reach sizes of up to 100 billion kilometers in height, which is a scale so large that it extends far beyond the size of the solar system. The formation of these waves comes from the interaction between the fast wind and the slower material that was expelled earlier when the star was losing mass at a slower rate. When the fast-moving wind collides with the older, slower-moving gas, the material is suddenly compressed and heated to very high temperatures. Atoms in these shock regions then emit visible light and infrared radiation, which makes the waves detectable by telescopes. The presence of such strong shocks is one reason the Red Spider Nebula displays its characteristic appearance. The central star of the nebula, now a white dwarf, is surrounded by a thick layer of dust that obscures some of its properties. Because the dust hides parts of the star, astronomers have to rely on indirect measurements to determine its temperature and composition. Estimates suggest that the surface temperature of this white dwarf is extremely high, most likely between 150,000 Kelvin and 250,000 Kelvin. However, some studies propose that the temperature could be even higher, perhaps around 340,000 Kelvin, or even as high as 500,000 Kelvin, values which would make it one of the hottest white dwarfs yet discovered. Objects with such temperatures emit strong ultraviolet radiation and produce ionized gas in large volumes. Observations using both the Hubble Space Telescope and the near-infrared camera of the James Webb Space Telescope revealed that there is also warm dust with temperatures around 1000 Kelvin located close to the star. The survival of dust so close to such a hot object suggests that complex interactions are occurring, possibly caused by the gravitational influence of a companion star or by a disk-like structure rotating around the central system. Researchers studying the central region have proposed that the star that originally formed the nebula experienced significant interactions with a close companion star during its late evolutionary stages. These interactions could include mass transfer, tidal forces, or the formation of a common envelope structure, all of which may shape the material being expelled into space. Some evidence suggests that the system may include a circumbinary disk, a rotating disk of gas and dust surrounding two stars orbiting close together. If such a disk exists, it could regulate how matter flows outward into the nebula and influence the shape of the lobes. Observations using X-ray telescopes such as the Chandra X-ray Observatory did not detect strong X-ray emissions from the central companion. This suggests that the companion star must be less massive than the Sun, because more massive stars would produce detectable high-energy radiation when interacting with a white dwarf, especially in a close binary system. The distance to the Red Spider Nebula is not known with complete certainty. Different estimates over the years have placed it around 1,900 light-years from Earth, or more likely somewhere between 3,000 and 8,000 light-years. This range arises because planetary nebula distances are notoriously difficult to measure. Methods rely on surface brightness, expansion rate, and assumptions about the nebula's physical properties, all of which can produce uncertainty. However, even at the lower end of estimates, the nebula is far enough away that its fine structure requires high-resolution imaging from observatories capable of resolving details smaller than an arc-second. A research group using instruments such as the Hubble Space Telescope, the Atacama Large Millimeter Submillimeter Array, the Chandra X-ray Observatory, and the James Webb Space Telescope performed a detailed study of the nebula's structure. They found that the central region of the nebula forms an irregular asymmetric ring or spiral-like shape with a radius of roughly 5 arcseconds, which corresponds to about 0.04 parsec when converted into physical units. This central region is surrounded by a dense torus of molecular material that lies along the equatorial plane of the system. This torus has a deprojected radius near 0.13 parsec and is inclined at about 38 degrees from our line of sight. The molecular torus expands outward at a speed of around 13 kilometers per second and is estimated to have been created roughly 10,000 years ago, which represents the age of the material currently observed in that structure. Imaging of molecular hydrogen gas provides a clearer picture of the larger lobes that extend outward from the central region. These lobes form closed, bubble-like shapes stretching to around 100 arcseconds in size, which corresponds to about 0.9 parsec when corrected for projection effects. The lobes show expansion speeds of about 300 kilometers per second. If one uses this expansion speed and the current size of the lobes to determine how long ago they were formed, the result gives a dynamical age of roughly 3,700 years for these structures. That means the fast and energetic phase that created the lobes occurred several thousand years after the formation of the equatorial torus, suggesting that the mass loss during the star's late stages was not uniform over time and likely involved multiple distinct episodes of outflow. When observed in light emitted by singly ionized iron, the lobes show an S-shaped pattern similar to the smaller scale symmetry seen in the overall bipolar structure. This S-shaped pattern is also observed in another nebula, NGC 6302, suggesting that similar physical mechanisms may operate in both objects. The ion emission likely comes from regions where fast winds collide with slower material, producing shocks that heat the gas to temperatures high enough to excite iron atoms. The presence of such shock-induced emission reinforces the idea that the White Spider Nebula was shaped by a collimated, focused stellar wind, possibly channeled by magnetic fields or a binary interaction. Strong shocks can form when a fast jet of material impacts denser gas located at the boundary of a lobe. The collision compresses the gas, raises its temperature, and accelerates particles to velocities that cause ionization. This in turn produces radiation in specific wavelengths that can be detected by telescopes equipped with the proper filters. The appearance of the nebula, with its extended lobes and shock-generated waves, provides important information about how stars similar in mass to the Sun evolve after exhausting their nuclear fuel. When a star like the Sun reaches the end of its life, it expands into a red giant and begins to lose large amounts of mass. Eventually, the outer layers are ejected into space, leaving behind a hot core that contracts into a white dwarf. As the core becomes exposed, its high temperature produces ultraviolet radiation strong enough to ionize the expelled gas, creating the glowing shell that we call a planetary nebula. The specific appearance of the nebula depends on many factors, including the mass of the star, its rotation rate, magnetic field, and any companion objects orbiting nearby. In the case of the Red Spider Nebula, the central star must have had either strong magnetic activity, a close companion, or both, because the outflows are highly organized rather than spherical. Spherical nebulae occur when material is expelled evenly in all directions, but the Red Spider Nebula displays a clear axis of symmetry and an equatorial dense region that restricts the flow of gas, forcing it to move preferentially along the poles. The extremely hot white dwarf in the center plays a major role in shaping the physical conditions of the surrounding gas. With a temperature potentially reaching several 100,000 Kelvin, the intense radiation emitted by the white dwarf ionizes hydrogen, helium, oxygen, nitrogen, and other elements in the nebula. Ionization removes electrons from atoms, and when those electrons recombine with ions, they emit light at specific wavelengths. This process explains much of the visible and infrared emission that telescopes observe. The high-energy radiation also breaks apart molecules and heats dust grains, causing them to emit in infrared wavelengths. Some of the detected dust persists near the star, which is unexpected given the harsh radiation environment. This implies that the dust may be shielded by a dense disk, or formed in regions where cooler material is present. The origin of this dust and why it remains stable at temperatures near 1000 Kelvin is still being studied. It may form from material supplied by the companion star, or may be leftover material that survives because of its orbit within a protected region of the disk. The nebula's location near the center of the Milky Way adds further interest, because the dense stellar environment in that region contains strong gravitational influences, higher background radiation fields, and more interstellar material than in areas located farther out in the galactic disk. The interstellar environment around the Red Spider Nebula may therefore interact with the expanding lobes. If the nebula encounters dense interstellar clouds or magnetic structures in the central region of the galaxy, this could alter its shape or slow its expansion in certain directions. Signals of asymmetry and irregularities in the lobes could represent such interactions. Studying these interactions helps astronomers understand how stellar ejecta mix with the interstellar medium and contribute new elements into the galaxy. Planetary nebulae play an important role in enriching the galaxy with carbon, nitrogen, and other elements produced during the star's red giant phase. Understanding how these elements spread into the interstellar medium provides information about chemical evolution across the Milky Way. The structure of the Red Spider Nebula also provides clues about the mass-loss history of the progenitor star. During its evolution, the star likely experienced phases of slow winds during the red giant stage, followed by faster and more energetic winds during the early white dwarf stage. The slower winds formed dense shells of material that remained close to the star, while the faster winds caught up with these shells and swept them outward, creating shock fronts. By measuring the speed and position of these shells, astronomers can reconstruct the sequence of events that occurred during the last several thousand years of the star's life. The fact that the equatorial torus is older than the polar lobes suggests that the equatorial material was ejected during an earlier phase, possibly when the envelope of the star expanded and became unstable. The polar lobes likely formed later, when the core became hotter and drove a faster wind capable of breaking through the equatorial region and escaping along the poles. This kind of time sequence is important for testing models of late stellar evolution. The possible presence of a binary companion introduces additional complexity to the system. If the companion star orbits close to the white dwarf, the gravitational forces between them could create tidal interactions that shape the outflowing gas. In some systems, the companion may even enter the expanding envelope of the primary star, forming a common envelope system. During this stage, the companion spirals inward through the envelope, depositing energy and angular momentum into the surrounding gas. This process can eject large amounts of material and form disk-like or bipolar structures. When the envelope is completely ejected, the remaining system may consist of a close binary pair embedded in a planetary nebula. Observational evidence such as the asymmetric ring, the equatorial torus, and the S-shaped lobe suggests that a binary interaction is likely in the case of the Red Spider Nebula. If the companion were more massive than the Sun, it would likely produce X-ray radiation when interacting with the white dwarf, but no such radiation has been detected, supporting the idea that the companion is a low-mass star. Understanding systems like the Red Spider Nebula helps scientists predict what will happen to the Sun several billion years from now. when it exhausts the hydrogen in its core and evolves into a red giant. The Sun will eventually shed its outer layers and form a planetary nebula, leaving behind a white dwarf. Although the Sun does not have a close stellar companion, it may still form structures shaped by rotation, magnetic fields, or interactions with planets. By studying planetary nebulae with different shapes and central star conditions, astronomers can determine the range of possible outcomes for stars of different masses and environments. The Red Spider Nebula represents an extreme example, with very hot winds and strong shocks that may not occur in the Sun's future nebula. However, the basic physical processes are similar: ionization of gas, expansion of shells, formation of shock fronts, and the development of structures influenced by surrounding material. The precision of instruments such as the James Webb Space Telescope allows astronomers to study small-scale features that were previously too faint or too small to detect. For example, the ripples in the lobe walls and the fine patterns in the central ring provide data for fluid dynamic models of expanding ionized gas. The ability to map dust temperatures and compositions also helps researchers understand how dust forms in environments with intense ultraviolet radiation. Infrared instruments on the James Webb Space Telescope can detect molecules and dust grains that radiate at wavelengths invisible to optical telescopes. By combining data from multiple telescopes operating at different wavelengths, researchers can create detailed three-dimensional models of the nebula. Sagittarius B2, often abbreviated as SIR-B2, is a truly extraordinary region in our Milky Way galaxy, a place where the cosmos seems to gather in immense clouds of gas and dust to create new stars in breathtaking numbers. The James Webb Space Telescope, with its incredibly sensitive infrared instruments, has recently provided a window into this dazzling stellar nursery, revealing newborn stars shining brightly amidst thick clouds of cosmic dust, and exposing details that had never been seen before. This region, located about 120 parsecs, which is nearly 390 light-years from the very heart of our galaxy, represents one of the most massive and complex star-forming environments in the Milky Way. When we think about it in terms of sheer size, the cloud spans roughly 45 parsecs across, which translates to about 150 light-years, an almost incomprehensible scale of space where matter gathers to give birth to new suns. SGR-B2 is not merely a uniform cloud, it is a swirling, structured and highly varied environment. Its mass is staggering, estimated at around 3 million times the mass of our Sun, making it a giant among molecular clouds. Hydrogen atoms, the fundamental building blocks of stars, are extraordinarily dense here, averaging 3,000 per cubic centimetre, which is roughly 20 to 40 times denser than the average molecular cloud in the galaxy. This extreme density, combined with varying temperatures and complex internal structures, makes SGR-B2 a laboratory for understanding how stars and planetary systems are formed. The cloud is divided into three main cores, which astronomers have named the North Core, the Middle or Main Core, and the South Core. The North Core is known as SGR-B2, open parenthesis N close parenthesis, the middle as SGR-B2, open parenthesis M close parenthesis, and the southern as SGR-B2, open parenthesis S close parenthesis. Both the north and main cores are especially active in terms of star formation, hosting some of the most prolific regions in the galaxy, where stars are born in large clusters. Within these cores, astronomers first identified 10 H2 regions, which are areas of ionized hydrogen gas surrounding young hot stars. These regions were labelled from A through J for easier study. H2 regions A through G, along with I and J, are found within SGR-B2, open parenthesis M close parenthesis, the main core, while H lies in SGR-B2, open parenthesis S close parenthesis, and K is located in the northern core, SGR-B2, open parenthesis N close parenthesis. These regions are sites where the radiation from young stars is so intense that it ionizes the surrounding gas, creating vast glowing nebulae that shine brightly across different wavelengths of light. The central, 5 parsec wide core of SGR-B2 alone is emitting energy equivalent to approximately 10 million times the luminosity of the Sun, a staggering figure that underscores the sheer intensity of stellar activity occurring within this one small segment of the cloud. The chemical composition of SGR-B2 is equally fascinating. This cloud is rich in complex molecules, many of which are considered key ingredients in the chemistry that eventually leads to life. Among the molecules detected are alcohols such as ethanol and methanol, as well as vinyl alcohol. These compounds form when atoms collide and bond on the surfaces of tiny dust grains, creating larger and more complex molecules that are eventually released back into the surrounding cloud. One particularly interesting discovery was ethyl formate, a molecule that not only plays a role in the formation of amino acids, but also gives raspberries their distinctive flavour, prompting playful comparisons in scientific articles that suggest the cloud might smell like raspberry rum. In addition to these, astronomers have identified significant amounts of butyronitrile, also known as propyl cyanide and other alkyl cyanides, further highlighting the extraordinary molecular diversity of this region. Temperatures within SGRB2 vary widely depending on location. In the dense star-forming regions, temperatures reach approximately 300 kelvins, which is roughly 27 degrees Celsius, while in the more diffuse outer envelopes of the cloud, temperatures drop to 40 kelvins, equivalent to minus 233.2 degrees Celsius. These low temperatures, combined with the low pressures typical of interstellar space, make ordinary chemical reactions extremely slow. However, the presence of tiny dust grains, each with a silicon core surrounded by icy mantles containing water and carbon compounds, provides surfaces on which atoms and molecules can meet and react. These grains act as miniature chemical factories. Molecules accrete onto their surfaces, interact with neighbouring compounds, and eventually evaporate back into the cloud, enriching the surrounding space with new and more complex molecules. The molecular richness of SGRB2 has made it a key target for astronomers, using a variety of observational techniques. Much of the chemistry of the cloud can be observed at infrared wavelengths in the range of approximately 102 to 1003 micrometers. Remarkably, about half of all known interstellar molecules were first discovered in or near SGRB2, and nearly all other known molecules in space have since been detected in or around this massive cloud. The European Space Agency's Gamma Ray Observatory, Integral, has also contributed to our understanding of SGRB2 by observing gamma rays interacting with the cloud. This interaction produces X-ray emission, which has been traced back to a massive outburst from the supermassive black hole at the centre of the galaxy, Sagittarius A star, which occurred approximately 350 years ago. This outburst was estimated to have been 1,000,000 times more luminous than the black hole's current output. Japanese astronomers using the Suzaku satellite in 2011 confirmed these results by observing the X-ray glow from the galactic centre, providing further evidence of the powerful past activity of the central black hole and its effect on nearby molecular clouds like SGRB2. The James Webb Space Telescope has added even more detailed observations to this already remarkable picture. Using its infrared instruments, JWST has revealed candidate H2 regions that had been missed by previous radio observations. At wavelengths of approximately 25 micrometers, JWST detected infrared radiation escaping from the protocluster in the north core SGRB2 open parenthesis N close parenthesis, following the path of large-scale outflows of gas and dust. Interestingly, young stellar objects, or YSOs, that were previously detected with the Atacama Large Millimeter Submillimeter Array, ALMA, on the western side of the cloud, were not observed by JWST. However, JWST did detect the hot dust surrounding the outflows from these YSOs, providing indirect evidence of ongoing star formation activity. On the eastern side of the cloud, JWST's observations revealed regions of very recent star formation, highlighting the dynamic and continuous process of stellar birth taking place across the cloud. SGRB2 is not only a place of star formation, it is also a remarkable chemical laboratory. The complex molecules found in the cloud suggest processes that can lead toward the building blocks of life. The presence of alcohols, esters, and nitriles demonstrates that even in the harsh, cold, and tenuous environment of interstellar space, chemical complexity can flourish when the right conditions exist. The icy dust grains act as catalysts for chemical reactions, allowing molecules to form that could not readily form in the gas phase alone. These grains are coated with a mixture of water, simple carbon compounds, and other ices, and provide a platform where atoms and molecules collide, stick, rearrange, and form new species. When these molecules desorb or evaporate from the grain surfaces, they enrich the surrounding gas with increasingly complex chemistry, producing molecules that astronomers can detect with infrared and radio telescopes. The variability in temperature across SGRB2 creates a diverse range of environments within a single molecular cloud. In the hotter, dense cores, chemical reactions can proceed more rapidly, and stars can form relatively quickly. In contrast, in the colder, less dense envelopes, reactions are slowed down, but the dust grains allow complex molecules to form over longer timescales. This combination of hot and cold regions, dense and diffuse material, creates a patchwork of chemical and physical conditions, making SGRB2 an ideal natural laboratory for studying the processes that lead from simple atoms to complex molecules, and from clouds of gas to the formation of new stars and planetary systems. The discovery of molecules such as ethyl formate, responsible for the flavor of raspberries, and other compounds related to amino acids has profound implications for our understanding of prebiotic chemistry in space. These molecules suggest that the ingredients for life are not unique to Earth but are widespread throughout the galaxy, formed naturally in regions where dense molecular clouds like SGRB2 exist. The fact that half of all known interstellar molecules were first identified near SGRB2 underscores the importance of this cloud in the broader field of astrochemistry, and continues to make it one of the most studied and intriguing molecular clouds in the Milky Way. Gamma-ray and X-ray observations also reveal the dynamic interactions between SGRB2 and its environment. The past activity of Sagittarius A star, the supermassive black hole at the galactic center, sent energetic radiation outward, which is still being reflected and absorbed by clouds like SGRB hundreds of years later. These interactions illuminate the cloud in X-rays, providing astronomers with a snapshot of how energetic events at the galaxy's core can affect distant molecular clouds. This interplay between high-energy processes and star-forming regions demonstrates the interconnectedness of different parts of the galaxy, where events at the center influence the chemistry and physics of clouds hundreds of light-years away. JWST's infrared observations provide a complementary view of SGRB2. Infrared light penetrates the thick dust that often hides these regions from optical telescopes, revealing young stars still embedded in their birth clouds. JWST has identified previously unknown H2 regions and traced the paths of protostellar outflows, giving scientists a clearer picture of how material flows within the cloud, how stars gain mass from their surroundings, and how they influence the cloud through radiation and winds. These observations also help explain discrepancies between previous ALMA observations and new JWST data, showing that even when young stars themselves are hidden, the effects of their formation, such as heated dust, can be detected. The north core of SGRB2, designated N, has proven particularly rich in activity. Protoclusters there emit infrared radiation along paths carved by massive outflows, revealing how material is channeled away from forming stars. These outflows create cavities in the dense gas, allowing infrared light to escape and reach telescopes like JWST. Meanwhile, the western side, observed by ALMA, contains young stellar objects whose presence is inferred from the hot dust around their outflows rather than the stars themselves, while the eastern side shows evidence of very recent star formation, suggesting a staggered and ongoing process of stellar birth across the cloud. The mid-core, or main core M, continues to be a powerhouse of star formation, containing many of the previously identified H2 regions, A through G, I, and J. The radiation from these regions ionizes the surrounding hydrogen, creating bubbles of glowing gas that expand into the surrounding medium. The southern chorus, while less massive than the northern or main cores, still hosts H2 region H and contributes to the overall dynamic environment of the cloud. Chemical reactions within SGRB2 are facilitated by the surfaces of cold dust grains, which provide a platform for molecules to meet, bond, and form increasingly complex species. These processes are crucial for the formation of molecules that could serve as precursors to life, demonstrating that even in the frigid, tenuous environment of interstellar space, chemistry can proceed efficiently when aided by solid surfaces. Observations of molecules such as methanol, ethanol, vinyl alcohol, ethyl formate, and propyl cyanide illustrate the richness of this chemical environment and highlight the cloud's importance as a laboratory for understanding prebiotic chemistry in space. The interplay of density, temperature, radiation, and dust grains creates a highly structured and chemically diverse environment in SGRB2. Dense regions provide the material and energy for star formation, while dust grains allow complex molecules to form. Radiation from young stars and from the past activity of Sagittarius, a star shapes the cloud, influencing chemistry and driving the formation of new stars. Observations across the electromagnetic spectrum, from gamma rays and X-rays to infrared light, provide complementary insights into the cloud's structure, composition, and ongoing processes, revealing a dynamic and evolving environment that is both a stellar nursery and a chemical laboratory. The discovery of new candidate H2 regions by JWST demonstrates that even well-studied clouds like SGRB2 still have secrets to reveal. Infrared observations can penetrate dust-obscured regions, uncovering new sites of star formation that are invisible in radio or optical wavelengths. The detection of hot dust surrounding protostellar outflows provides additional evidence of ongoing star formation, while the identification of recent star formation on the eastern side of the cloud illustrates the continuous nature of stellar birth in this region. SGRB2 serves as a window into the earliest stages of star formation, showing how dense clouds of gas and dust collapse to form clusters of stars. The presence of complex molecules suggests that the ingredients for life can form naturally in these environments, offering a tantalizing glimpse of the chemical processes that may lead to the development of life elsewhere in the galaxy. Observations from JWST, ALMA, and other telescopes continue to provide new insights into this remarkable cloud, revealing the intricate interplay of physics, chemistry, and stellar activity that drives the evolution of the Milky Way. The combination of extreme density, varying temperatures, rich chemistry, and dynamic star formation makes SGRB2 a truly unique region in the galaxy. It is a place where gas and dust come together to form stars and planets, where complex molecules can form even under the harshest conditions, and where the past activity of the galactic center leaves its mark on the surrounding material. The cloud's size, mass, and complexity make it an unparalleled laboratory for studying the processes that govern star formation, molecular chemistry, and the evolution of galaxies, providing astronomers with an extraordinary natural experiment that is still revealing its secrets with each new observation. JWST's observations at 25 micrometers have revealed details that help map the flow of material within SGRB2. Protostellar outflows carve paths through the dense gas, allowing infrared light to escape and revealing the locations of newly forming stars. The hot dust surrounding outflows observed on the western side of the cloud shows that even when young stars are hidden, their energetic influence can still be detected. On the eastern side, newly formed stars illuminate their surroundings, providing evidence of recent and ongoing star formation that complements the observations of older H2 regions in the main and northern cores. The chemistry of SGRB2 is directly linked to its physical conditions. The variation in temperature and density across the cloud allows different chemical processes to dominate in different regions. In the denser, warmer cores, reactions proceed more quickly, forming complex molecules that can eventually be incorporated into forming stars and planetary systems. In the colder, less dense outer regions, chemical reactions are slower, but dust grains provide surfaces for molecules to interact, creating a rich tapestry of chemical diversity. Observations of molecules such as alcohols, nitriles, and esters reveal that SGRB2 is a site of complex chemical synthesis, making it a crucial target for astrochemists studying the origins of prebiotic molecules in space. The interactions between radiation, dust, and gas create a dynamic environment in which star formation is continuously regulated. High-energy radiation from past outbursts of Sagittarius A star illuminates the cloud, producing X-rays that can alter the chemistry of the gas. Radiation from newly formed stars ionizes hydrogen in H2 regions, creating bubbles of hot gas that expand into the surrounding medium, influencing the formation of subsequent generations of stars. Outflows from protostars shape the cloud, redistributing material and providing pathways for radiation to escape, while the dense, dusty cores act as reservoirs of material for future star formation. Observations of SGRB2 with JWST provide unprecedented detail, revealing how young stars interact with their surroundings. The detection of infrared radiation escaping along outflow paths shows how protostellar activity can clear cavities in dense gas, while the hot dust surrounding protostellar outflows indicates the presence of embedded YSOs that are otherwise invisible. These observations complement previous data from ALMA and radio telescopes, providing a more complete picture of the star formation processes within this massive molecular cloud. SGRB2's size and complexity mean that it contains a variety of environments within a single cloud. The dense cores provide sites for rapid star formation, while the more diffuse outer regions serve as reservoirs of material and sites for complex chemistry. The interplay between radiation, temperature, density, and dust grains creates a rich and varied landscape in which stars are continuously forming, evolving, and influencing their surroundings. Observations across multiple wavelengths, from gamma rays to infrared light, reveal different aspects of the cloud's structure and activity, highlighting the importance of multi-wavelength astronomy for understanding these complex regions. The discovery of complex molecules combined with the detailed mapping of star-forming regions underscores the importance of SGARB2 for understanding the processes that govern the formation of stars and planetary systems. The presence of molecules such as ethanol, methanol, vinyl alcohol, ethyl formate, and propyl cyanide demonstrates that the cloud is a chemical laboratory of extraordinary richness. These molecules are formed through a combination of gas phase reactions and surface chemistry on dust grains, illustrating the diverse pathways through which complex chemistry can occur in space. JWST's ability to detect infrared radiation from protostellar outflows and newly forming stars provides a critical tool for mapping the dynamics of SGARB2. The identification of candidate H2 regions that were missed in previous radio surveys shows the power of infrared observations for uncovering hidden star-forming regions. The detection of hot dust around protostellar outflows provides evidence of ongoing star formation, even in regions where the young stars themselves are obscured by dense dust. This information helps astronomers understand how stars accumulate mass, how they influence their surroundings, and how clusters of stars form within massive molecular clouds. The cloud's complex internal structure, with its three main cores and numerous H2 regions, illustrates the hierarchical nature of star formation in massive molecular clouds. Dense cores provide the material and conditions necessary for star formation, while feedback from young stars such as radiation, winds, and outflows shapes the surrounding environment and influences subsequent generations of stars. The variation in chemical composition, temperature, and density across the cloud further contributes to its complexity, creating a rich and dynamic environment in which stars and molecules form together, interacting in ways that are only beginning to be fully understood. SGARB2 is also a remarkable record of past events in the galaxy. The reflection of high-energy radiation from Sagittarius A star's past outbursts provides a glimpse into the history of the galactic center, showing how energetic events can leave imprints on molecular clouds hundreds of light-years away. These interactions influence the cloud's chemistry, structure, and star formation activity, illustrating the interconnectedness of galactic processes. Observations of X-ray emission, combined with infrared and radio data, provide a multifaceted view of the cloud, revealing both its current activity and its response to past events in the galaxy. The ongoing study of SGARB2 continues to reveal new details about the birth of stars, the formation of complex molecules, and the influence of galactic events on star-forming regions. JWST's infrared observations, combined with data from ALMA, Integral, and other telescopes, provide an unprecedented view of this extraordinary cloud. Each new observation adds to our understanding of the processes that govern the formation of stars and the evolution of molecular. The discovery of dark beads on Saturn has opened an entirely new window into the mysteries of the ringed planet, revealing a phenomenon unlike anything seen before in our solar system. These dark beads appear as small, distinct features scattered within Saturn's otherwise luminous auroral halos, which themselves are dazzling displays of light encircling the planet's polar regions. Unlike the familiar auroras of Earth, which shimmer in green, red, and purple due to the interaction of solar wind particles with our atmosphere, Saturn's auroras are larger, brighter, and more complex, shaped by the immense magnetic field that the planet generates through its rapid rotation and metallic hydrogen interior. The James Webb Space Telescope, with its incredibly sensitive infrared and near-infrared instruments, has now revealed these new dark structures as subtle interruptions in the glow, marking a phenomenon that is both mysterious and captivating. The first thing to note about these dark beads is their appearance. They are dark in contrast to the bright auroral glow that surrounds them. When astronomers first examined the infrared images from the telescope, the beads stood out immediately, appearing like tiny voids or shadows embedded within the luminous bands of light circling Saturn's poles. Their darkness is not absolute. They do not absorb all light, nor do they appear like solid objects, but rather they represent regions where the auroral emission is diminished or altered, suggesting that something in Saturn's atmosphere is interfering with the normal processes that create auroral light. This discovery is significant because, until now, auroral features on planets have been mostly understood as relatively uniform or smoothly varying regions, shaped by the flow of charged particles along magnetic field lines. The dark beads challenge this understanding by introducing discrete, coherent structures that behave in ways that are not yet fully understood. The current leading theories propose that these dark beads arise from complex interactions between Saturn's atmosphere and its magnetic field. Saturn has one of the strongest magnetic fields in the solar system, second only to Jupiter, and this field is generated deep within the planet, where metallic hydrogen conducts electricity and creates a powerful dynamo. As charged particles from the solar wind, or from the planet's own magnetosphere, travel along magnetic field lines, they collide with molecules in the upper atmosphere, exciting them and producing the brilliant auroral glow. The dark beads suggest that in certain localized areas, something disrupts this energy transfer, causing the auroral emission to be dimmed or modified. The specific mechanisms could involve variations in the density or composition of the upper atmosphere, localized electric currents, or turbulent interactions between different layers of charged particles. Some scientists speculate that these beads may represent areas where the magnetic field lines are twisted or concentrated, altering the flow of energy and creating the distinctive dark appearance. One remarkable aspect of the dark beads is their dynamic yet stable nature. Observations show that these features can persist for hours, maintaining their shape and position even as the planet rotates rapidly on its axis. Saturn spins once approximately every 10 hours and 33 minutes, a rotation so fast that it flattens the planet slightly at the poles and stretches the equator outward. The fact that the dark beads remain coherent through this rotation suggests that the processes creating them are robust and deeply connected to the structure of the magnetic field, rather than being transient or fleeting atmospheric phenomena. At the same time, subtle changes in the size, shape, and brightness of the beads indicate that they are not static. They are constantly influenced by the flow of energy, the motion of charged particles, and the planet's powerful winds. Saturn's winds are among the fastest in the solar system, reaching speeds of over 1,500 km per hour near the equator. These winds could help shape and modulate the beads, sweeping charged particles and atmospheric material into patterns that give the beads their distinctive dark appearance. Importantly, the dark beads are not thought to result from material falling into the atmosphere from outside the planet. Saturn, like all the gas giants, is surrounded by rings and a retinue of moons, and it does encounter meteoroids and cosmic dust that can enter its upper atmosphere. However, the size, distribution, and temporal behavior of the dark beads do not match the patterns one would expect from infalling material. Instead, the evidence points to an internally driven mechanism, rooted in the interaction between the planet's magnetic field and its upper atmospheric layers. This makes the beads a phenomenon that is both planetary and atmospheric in origin, revealing the intricate and sometimes surprising ways in which a giant planet's internal dynamics can influence its visible features. The discovery of the dark beads also has implications for our understanding of auroras more broadly. On Earth, auroras are shaped by the planet's magnetic field and the solar wind, but the scale is relatively small and the structures are often ephemeral, changing over minutes. On Jupiter, auroras are much larger and more powerful, influenced by the planet's rotation and the volcanic activity of the moon Io, which injects plasma into the magnetosphere. Saturn now presents a different case entirely. A giant, rapidly rotating planet with a strong magnetic field and a complex atmosphere in which discrete dark features can persist within auroras. Studying these beads can provide scientists with new insights into how magnetic fields interact with atmospheric gases, how energy is transported and dissipated in planetary atmospheres, and how large-scale planetary dynamics create observable phenomena. This, in turn, can inform our understanding of exoplanets with strong magnetic fields or dynamic atmospheres, expanding the knowledge gained from our own solar system to worlds orbiting distant stars. The spatial distribution of the beads is also fascinating. Early images suggest that they appear in clusters or chains within the auroral halo, sometimes aligned along specific latitudes or following patterns that hint at underlying magnetic structures. This clustering could indicate that certain regions of Saturn's magnetosphere are more prone to the processes that create the beads, perhaps due to variations in field strength, particle density, or atmospheric composition. Alternatively, the beads might trace lines of electrical current flowing through the upper atmosphere, revealing a hidden network of energy transfer that is normally invisible to telescopes. Each bead, while small compared to the planet as a whole, may be the visible tip of a much larger and more complex process, one that extends deep into the magnetosphere and into the atmospheric layers below the auroras. Observing the beads requires the extraordinary capabilities of the James Webb Space Telescope. Traditional telescopes, whether on Earth or in orbit, are limited in their ability to detect subtle infrared features in the glare of a giant planet. Webb's instruments, designed to capture extremely faint infrared light with high spatial resolution, allow astronomers to see not only the broad auroral glow, but also the fine-scale variations within it. The dark beads would likely have gone unnoticed without this combination of sensitivity and resolution, demonstrating the importance of advanced observational technology in uncovering new phenomena in familiar planetary environments. As the telescope continues to monitor Saturn over time, it will provide additional data on the temporal evolution of the beads, helping scientists distinguish between transient events and stable atmospheric structures, and allowing them to refine models of how energy flows through the planet's magnetic field and atmosphere. Another intriguing possibility is that the dark beads could be linked to interactions between Saturn's auroras and its ionosphere, the electrically charged layer of the upper atmosphere. On Earth, ionospheric currents can influence the shape and brightness of auroras, creating regions of enhanced or diminished light. If similar processes occur on Saturn, the dark beads might represent areas where electrical currents are particularly strong, redirecting energy and altering the emission of light. These interactions would provide a unique window into the electrical environment of a giant planet, revealing the ways in which charged particles, magnetic fields, and atmospheric gases combine to produce observable features. The chemical composition of the atmosphere in regions with dark beads may also play a role. Saturn's upper atmosphere is composed primarily of hydrogen and helium, but it contains trace amounts of methane, ammonia, water vapor, and other molecules that can influence how auroral light is produced. Variations in these trace gases, or in the temperature and pressure of the atmosphere, could change the efficiency of energy transfer from charged particles to photons, producing localized dimming that appears as dark beads. Future observations with Webb and other telescopes, including spectroscopic measurements, may help identify whether chemical or physical differences in the atmosphere are responsible for the phenomenon, or whether it is entirely driven by magnetic and electrical effects. In addition to their scientific significance, the dark beads are visually striking. The contrast between the deep darkness of the beads and the brilliant light of the surrounding auroras creates a pattern that is both mesmerizing and mysterious. In some images, the beads appear like a string of pearls encircling the pole, while in others they seem scattered like cosmic seeds across the auroral canvas. This aesthetic aspect, while secondary to the scientific importance, captures the imagination and highlights the fact that even familiar planets like Saturn can still surprise us with beauty and complexity at scales both large and small. The discovery also raises questions about whether similar features might exist on other planets. Jupiter's auroras, for example, are even more powerful than Saturn's, and are shaped by the planet's own magnetic environment, as well as the volcanic plasma from its moon Io. Could Jupiter host analogous dark features within its auroras, perhaps shaped by its unique magnetic and atmospheric dynamics? Likewise, could exoplanets with strong magnetic fields and dynamic atmospheres exhibit auroral beads of their own, detectable with next-generation telescopes? The discovery on Saturn encourages scientists to look for patterns that were previously unimagined, and to consider new mechanisms by which planetary magnetism and atmospheric physics interact to produce visible phenomena. The temporal behavior of the beads is another area of active investigation. While the features appear stable over periods of several hours, longer-term observations are needed to understand whether they persist over days, weeks, or even longer, and whether they exhibit seasonal variations. Saturn has a long orbital period of approximately 29 Earth years, and its polar regions experience significant changes in sunlight over this period, affecting atmospheric circulation and possibly auroral activity. Observing the dark beads across different seasons could reveal how solar illumination planetary tilt and magnetospheric conditions influence their formation and evolution, providing deeper insights into the interplay between external and internal drivers of planetary phenomena. Finally, the dark beads underscore the continuing importance of exploration and observation in planetary science. Despite centuries of study, Saturn remains a world full of surprises, and the James Webb Space Telescope is revealing layers of complexity that were previously hidden. By studying these features in detail, scientists can probe fundamental questions about magnetic fields, atmospheric dynamics, energy transfer, and the behavior of charged particles in extreme environments. Each new observation builds a richer picture of the planet, illustrating how even a single phenomenon, dark beads in auroral halos, can open doors to understanding processes that govern not only Saturn, but the broader solar system and potentially distant exoplanets. The study of the dark beads is ongoing, and each new image and data point brings additional questions and hypotheses. Researchers continue to monitor the beads, analysing their distribution, brightness, temporal evolution, and possible connections to underlying atmospheric and magnetic processes. By combining infrared observations with models of Saturn's magnetosphere, atmospheric dynamics, and auroral physics, scientists hope to unravel the exact mechanism behind these mysterious features. What is already clear is that the beads represent a novel aspect of planetary auroras, a phenomenon that challenges existing knowledge and provides a tantalizing glimpse into the complex interactions that govern the behavior of giant planets in our solar system. The implications of these discoveries extend beyond Saturn itself. By understanding how dark beads form and persist, scientists gain insight into the general principles of planetary magnetism, atmospheric dynamics, and auroral physics, knowledge that can be applied to other planets both within and beyond our solar system. Moreover, the discovery highlights the power of modern telescopes, like the James Webb Space Telescope, to reveal phenomena that were invisible to previous generations of instruments. Each new detail adds to our understanding of the cosmos, reminding us that even familiar planets can hold surprises that challenge our ideas and inspire our curiosity. The dynamic interplay between Saturn's magnetic field, atmosphere, and auroral processes, as revealed by the dark beads, represents a frontier in planetary science. Understanding this interplay requires a synthesis of multiple disciplines, including magnetohydrodynamics, atmospheric chemistry, plasma physics, and observational astronomy. By studying the beads, scientists are learning how magnetic energy can shape atmospheric phenomena, how charged particles are accelerated and guided, and how large-scale planetary rotation and winds influence localized features. These lessons have the potential to inform our understanding of not only gas giants, but also the atmospheres and magnetospheres of exoplanets, especially those that are massive, rapidly rotating, and magnetically active. The continued investigation into dark beads promises to illuminate the subtle mechanisms that operate in extreme planetary environments. With each observation, the beads offer clues about the forces at play in Saturn's upper atmosphere, the structure of the planet's magnetic field, and the pathways through which energy flows and redistributes itself. They also demonstrate that auroras are not uniform glows but can contain fine-scale, intricate patterns that reflect the underlying physics of the planet. The beads stand as a testament to the ongoing surprises that await in the study of our solar system's giant planets, emphasizing that even a single discovery can open new avenues of scientific exploration and expand the boundaries of our knowledge. Webb's continuing observations will likely reveal more about the frequency, variability, and physical characteristics of the dark beads, helping scientists refine their models and perhaps discover related phenomena elsewhere on Saturn or on other planets. Each additional dataset provides a new piece of the puzzle, bringing researchers closer to understanding the precise combination of magnetic, atmospheric, and energetic factors that produce these striking features. As the telescope observes Saturn over extended periods, it may capture the formation and dissipation of beads, track their motion along magnetic field lines, and detect subtle interactions with atmospheric winds and ionospheric currents. This comprehensive view could ultimately explain why these beads appear in certain regions, persist for specific periods, and maintain their distinct appearance despite the rapid rotation and extreme dynamics of the planet. Saturn's dark beads, therefore, represent more than just a visual curiosity. They are a window into the deep and complex interactions that govern the behavior of a giant planet. They exemplify how energy, magnetism, and atmospheric dynamics intersect to produce phenomena that are observable across millions of kilometers, and they challenge astronomers to rethink assumptions about how auroras form and evolve in extreme planetary environments. The beads encourage a holistic view of planetary science, where magnetospheric physics, atmospheric chemistry, and observational astronomy must all come together to explain even the smallest features. As such, they symbolize both the progress made in understanding our solar system and the enduring mysteries that continue to drive exploration and discovery in planetary science. The dark bead's emergence within Saturn's auroral halos also prompts consideration of the interactions between internal and external factors affecting the planet. While internal factors include the magnetic field, rapid rotation, and atmospheric circulation, external influences such as the solar wind, interplanetary magnetic fields, and occasional cometary or meteoroid interactions could modulate the intensity and configuration of auroral phenomena. Studying the beads over time allows astronomers to tease apart these influences, revealing which aspects of the auroral formation are intrinsic to Saturn and which are responses to the broader space environment. The phenomenon also underscores the complexity of planetary atmospheres in general. Unlike terrestrial planets, gas giants like Saturn do not have a solid surface to anchor atmospheric processes. Instead, their atmospheres extend thousands of kilometers deep, with varying pressure, temperature, and chemical composition at different altitudes. The dark beads may form at specific altitudes where charged particle interactions, magnetic field configuration, and atmospheric composition intersect in a delicate balance. Understanding this balance can provide insight not only into auroras but also into the broader dynamics of Saturn's atmosphere, including its zonal winds, vortices, and large-scale circulation patterns. The interplay between observation and theory is crucial in studying the dark beads. The observational data provided by the James Webb Space Telescope gives astronomers a detailed view of the phenomenon, but interpreting these observations requires sophisticated modelling. Theoretical simulations of Saturn's magnetosphere, auroral processes, and atmospheric dynamics can help explain why the beads appear in certain locations, why they maintain coherence over time, and how they interact with other features of the auroral halo. This combination of high-resolution imaging and advanced modelling represents the cutting edge of planetary science, demonstrating how new technology enables discoveries that challenge and expand existing scientific paradigms. In addition to scientific modelling, comparisons with auroral phenomena on other planets help contextualize the dark beads. While Earth's auroras are relatively transient and confined to high latitudes, and Jupiter's are extraordinarily energetic and influenced by the volcanic activity of Io, Saturn offers a middle ground in scale, energy, and complexity. By comparing and contrasting these planetary auroras, scientists can begin to identify universal principles that govern the interaction between magnetic fields and atmospheres, while also recognizing the unique characteristics that make each planet's auroras distinct. The dark beads, as a newly discovered feature, add a fresh dimension to this comparative planetary perspective. The discovery has also sparked interest in potential future missions to Saturn that could provide in situ measurements of the auroral regions and their interactions with the magnetic field. While telescopic observations from Webb provide unprecedented detail, sending a spacecraft equipped with particle detectors, magnetometers, and atmospheric probes could reveal the physical and chemical conditions that create the dark beads in real time. Such missions would complement the remote observations, allowing scientists to link visual features to specific atmospheric and magnetospheric processes, and to understand the beads' formation in a way that is currently only inferred from images and models. The dark beads also invite reconsideration of how energy is distributed within Saturn's upper atmosphere. The auroras themselves are manifestations of energy deposition from charged particles, and the beads may indicate localized regions where energy is either enhanced or suppressed. By mapping the beads over time and correlating their positions with models of particle precipitation and magnetic field lines, scientists can gain insight into the pathways of energy flow within the auroral region. This could illuminate processes that are fundamental to planetary atmospheres, including the transfer of energy from the magnetosphere to the atmosphere and the resulting thermal and chemical effects. The discovery of the cosmic owl, a peculiar pair of colliding ring galaxies that visually resemble the face of an owl, represents one of the most remarkable observations in extragalactic astronomy in recent years. This extraordinary system, observed at a redshift of 1.14, places it at a staggering distance of approximately 8,800,000,000 light-years from Earth. At such distances, the light we are seeing today embarked on its journey through the universe roughly 8,800,000,000 years ago, a time when galaxies were undergoing some of their most dramatic evolutionary stages. The cosmic owl is not merely a striking visual curiosity in the sky. It is a cosmic laboratory that allows astronomers to study a wide range of physical processes in action, from galactic collisions to star formation, the growth of supermassive black holes, and the propagation of energetic jets across intergalactic space. At first glance, the cosmic owl presents a structure that is both whimsical and scientifically significant. The two nearly identical ring galaxies form what can be interpreted as the eyes of the owl, while the merging region, where gas, stars and dust from both galaxies interact intensely, forms the beak. This alignment is not coincidental but a direct result of a head-on collision between two galaxies of very similar mass and structure. Collisions of this nature are extremely dynamic and produce a range of physical phenomena that allow researchers to test models of galaxy evolution in exquisite detail. The cosmic owl, therefore, is not just a visual spectacle, but an invaluable natural experiment in the study of galactic dynamics, star formation processes, and the interplay between massive black holes and their host galaxies. Galaxy mergers such as the one observed in the cosmic owl are fundamental to understanding how galaxies evolve over cosmic time. When galaxies collide and merge, their gravitational interactions cause profound redistribution of stars, gas, and dust. The motions of stars within the galaxies, referred to as stellar kinematics, are significantly affected. Stars are displaced, orbits are altered, and sometimes entire stellar populations are scattered or absorbed into new configurations. Gas within the galaxies is compressed and shocked during the collision, often triggering waves of star formation known as starbursts, which are rapid periods of stellar birth that can drastically change the appearance and stellar content of the galaxies involved. Over millions to billions of years, these interactions contribute to the gradual assembly of stellar mass, reshaping the morphology of the galaxies from disk-like or spiral forms into more spheroidal or elliptical structures, depending on the specific parameters of the merger. In certain rare cases, galaxy mergers can produce what are called collisional ring galaxies. These are galaxies in which a nearly head-on collision with another galaxy causes a wave of gas and stars to move outward from the centre, forming a circular or nearly circular ring. Such rings are relatively rare in the local universe, with only a few hundred examples known to astronomers. The formation of these rings depends on a precise alignment and relative velocity between the colliding galaxies. When one galaxy plunges through the disk of another, the resulting gravitational shock waves push the gas and stars outward in a symmetric pattern, creating a spectacular ring that can be observed across vast cosmic distances. Collisional ring galaxies are of particular interest to astronomers because they provide a clear observational signature of a galaxy collision and allow researchers to study the effects of such high-energy interactions on both gas and stellar populations. The cosmic owl represents a truly exceptional case in this context. It is not a single ring galaxy resulting from a collision, but a pair of ring galaxies undergoing a merger. This means that two massive disks, each with a collisional ring structure, are interacting and merging simultaneously. Such a configuration is incredibly rare, and provides astronomers with a unique opportunity to observe multiple high-energy processes at once. The discovery was led by Mingyu Li of Tsinghua University in Beijing, China, and was made using a combination of the most advanced astronomical instruments available today, including the James Webb Space Telescope, the Atacama Large Millimeter Submillimeter Array, and the Very Large Array. The serendipitous detection of such a rare system highlights both the power of modern observational technology and the richness of the distant universe, where violent interactions like this were more common in the early stages of galaxy evolution. Deep imaging and spectroscopy from these instruments revealed a complex system of twin collisional ring galaxies, exhibiting nearly identical morphology. The symmetry of the rings in the cosmic owl suggests that the collision that created this system was nearly head-on, with the galaxies having similar masses and internal structures. The observed ring diameters are approximately 26,000 light-years each, which is comparable to the size of the Milky Way's stellar disk, emphasizing the vast scale of this interaction. Stellar mass estimates for the entire merging system indicate a total of about 320 billion solar masses. while the supermassive black holes at the centers of the two galaxies have estimated masses of around 67 million and 26 million solar masses respectively. These black holes play a crucial role in shaping the dynamics of the galaxies, particularly through their associated active galactic nuclei, which inject enormous amounts of energy into their surroundings. The detailed observations reveal that the compact cores of each galaxy form the eyes of the cosmic owl, while the region between them, brightened by intense star formation, younger stellar populations and nebular emission, forms the beak. This central zone is not merely decorative but is a site of energetic processes that illuminate the ongoing merger. The gravitational interaction between the galaxies compresses gas in this region, triggering bursts of star formation. New, massive stars shine brightly in ultraviolet and optical light, while the surrounding gas is ionized, producing characteristic emission lines that can be detected by sensitive instruments. This combination of young stars and glowing nebulae creates the distinct blue coloration seen in imaging, which visually completes the owl-like appearance. In addition to the spectacular visual structure, the cosmic owl hosts powerful active galactic nuclei in both galaxies. One particularly notable feature is the presence of a bipolar radio jet extending from the northwestern galaxy's nucleus. Such jets are streams of highly energetic particles propelled at nearly the speed of light by the supermassive black hole at the galaxy's center. In this case, the jet appears to extend toward the central merger zone, interacting with gas and stars along the collision front. This interaction induces additional shocks and turbulence, further influencing star formation and the evolution of the system. Jets like this provide a window into the complex feedback processes that regulate galaxy growth, showing how energy released by black holes can shape the distribution and dynamics of gas on scales of tens of thousands of light-years. The cosmic owl's dual ring structure provides a rare opportunity to study multiple aspects of galaxy interaction simultaneously. Observing the system allows astronomers to examine how head-on collisions produce collisional rings, how these rings evolve over time, and how interactions between two rings influence gas dynamics and star formation. Additionally, the combination of active galactic nuclei and collisional starbursts offers a natural laboratory for studying feedback processes, where energy from central black holes can trigger or suppress star formation in surrounding regions. The precise alignment and symmetry of the rings also allow researchers to test numerical simulations of galaxy collisions, helping to refine models of how mass, angular momentum, and energy are redistributed during such events. The implications of studying systems like the cosmic owl extend far beyond this single galaxy merger. Observations of colliding galaxies at a redshift of 1.14 allow astronomers to look back to a time when the universe was less than half its current age, roughly 4.5 billion years old. This era was a period of heightened galaxy interactions, as galaxies were closer together and more gas-rich than they are today. By studying the cosmic owl, scientists can gain insights into the processes that governed galaxy evolution in the early universe, shedding light on how today's galaxies, including the Milky Way, came to acquire their present shapes and stellar populations. Collisions like the one observed in the cosmic owl likely played a crucial role in shaping the distribution of stellar mass and the growth of supermassive black holes across cosmic time. The combination of observational techniques employed in studying the cosmic owl demonstrates the power of modern multi-wavelength astronomy. The James Webb Space Telescope provides deep infrared imaging and spectroscopy, revealing the distribution of stars, dust, and ionized gas even in regions obscured by dust. The Atacama Large Millimeter Chush Submillimeter Array contributes high-resolution measurements of cold gas, allowing researchers to trace molecular clouds and star-forming regions. Meanwhile, the Very Large Array offers insights into radio emission, highlighting the presence of jets and other energetic phenomena associated with active galactic nuclei. Together, these instruments allow for a holistic understanding of the processes occurring in this extraordinary system. In studying the cosmic owl, astronomers can observe several key astrophysical phenomena occurring in tandem. Collisional starbursts arise from the compression of gas during the interaction, producing bursts of new star formation. The active galactic nuclei inject energy into the surrounding medium, while jets from these nuclei interact with gas, creating shocks and additional star formation. The collisional ring structures themselves provide evidence of the near head-on nature of the collision, illustrating how specific gravitational configurations can produce highly ordered structures even in violent interactions. By examining all these processes within a single system, researchers can test theoretical models of galaxy evolution with unprecedented precision, comparing predictions about star formation rates, gas dynamics, and black hole growth to actual observations. Furthermore, the study of dual collisional ring galaxies like the cosmic owl allows astronomers to better understand the conditions that give rise to such rare structures. While single collisional ring galaxies are uncommon in the local universe, pairs of ring galaxies undergoing merger events are exceedingly rare, with only a handful expected to exist in any given cosmic volume. The symmetry and size of the rings in the cosmic owl provide strong evidence for a head-on collision between galaxies of similar mass and structure, offering a textbook case for studying the mechanics of collisional ring formation. The system's stellar mass, totaling roughly 320 billion solar masses, and the black hole masses of 67 million and 26 million solar masses, further underscore the scale and significance of the event. The visual resemblance to an owl is not merely coincidental but emerges naturally from the physical processes at work. The cores of the galaxies appear as eyes because they remain compact and relatively undisturbed, while the central merger zone forms the beak as a result of gas compression, star formation, and the interaction of energetic jets. The luminous blue emission from newly formed stars and ionized gas highlights this central region, making the owl-like appearance even more striking. This visual feature provides an accessible point of reference for public interest in science communication, drawing attention to the dramatic and beautiful outcomes of galactic collisions. The study of galaxy mergers like the cosmic owl also contributes to a broader understanding of cosmic structure formation. As galaxies merge and interact, they influence not only their immediate surroundings, but also the large-scale distribution of matter in the universe. Gas flows, tidal forces, and energetic feedback from black holes can extend over hundreds of thousands of light-years, affecting neighbouring galaxies in the intergalactic medium. These interactions help to shape the cosmic web, the vast network of galaxies and dark matter that forms the large-scale structure of the universe.